66 million years ago, on an otherwise ordinary spring morning in what would become Mexico's Yucatan Peninsula, the world was about to change forever. Dinosaurs had ruled Earth for over 165 million years, a reign so long it makes human civilization look like a mere footnote. Yet in a single hour, everything they knew would begin to unravel. The Chicxulub asteroid, a mountain of rock roughly 6 miles wide traveling at 45,000 miles per hour, was already slicing through Earth's atmosphere. Scientists now understand this final hour in remarkable detail through decades of geological evidence, computer simulations, and fossil records. The asteroid's shadow hadn't yet fallen across the landscape. Triceratops still grazed coastal plains. Pterosaurs soared above ancient seas. Tyrannosaurus stalked inland forests. None of them knew that within 60 minutes, the most catastrophic event in 250 million years would reshape every ecosystem on the planet and rewrite the future of life itself. Earth, 66 million years ago, was a planet almost unrecognizable to modern eyes. The continents occupied radically different positions on the globe. Fragments of the ancient supercontinent Pangaea had completed their long divorce, drifting apart to create oceans that would eventually become the Atlantic and Indian. North America itself was split in two by a vast inland sea called the Western Interior Seaway, stretching from the Arctic Ocean down to the Gulf of Mexico and dividing the continent into eastern Appalachia and western Laramidia. South America had separated from Africa, though Australia remained stubbornly attached to Antarctica. India was an island continent racing northward on a collision course with Asia that wouldn't conclude for millions more years. The world map was still a work in progress. What truly set this era apart wasn't geography alone, but climate. The late Cretaceous was a greenhouse world operating under fundamentally different atmospheric rules than today. Sea levels stood 200 to 250 meters higher than the present, drowning vast stretches of what would become dry land and creating shallow seas that covered roughly 1/3 of Earth's current land area. This dramatic flooding resulted from the displacement of ocean water by expanding mid-oceanic ridges and the near-total absence of polar ice caps. At high southern latitudes, regions equivalent to modern Antarctica's frigid coastlines, sea surface temperatures ranged between 27 and 37 degrees Celsius, conditions as warm as tropical waters today. Where icy wilderness now dominates, warm currents once circulated freely. The atmosphere itself carried a different chemical signature. Atmospheric carbon dioxide concentrations fluctuated between approximately 150 and 650 parts per million during the Barremian through Santonian interval, with estimates averaging around 300 ppm, comparable to pre-industrial Earth, but still elevated enough to sustain the hothouse conditions. Some research examining amber-trapped air bubbles suggests oxygen levels may have reached 25 to 35%, significantly higher than today's 21%, though this finding remains debated. If accurate, the supercharged atmosphere would have supported larger body sizes and more energetic metabolisms across many species. The air tasted different then. Weather patterns reflected this warmth. There was no permanent ice anywhere on the planet, no glaciers grinding across polar landscapes, no frozen caps reflecting sunlight back into space. Instead, coniferous rainforests stretched toward both poles, their canopies sheltering ecosystems that blurred the lines between temperate and tropical. Seasonal temperature variations existed, but operated within a narrower band than modern extremes. The global thermostat was set to hot and locked there by geologic forces beyond any creature's control. This was the stage upon which the final act of the Mesozoic era would play out. A world of warmth and plenty, utterly unprepared for what approached from the darkness of space. Across this warm, flooded world, dinosaurs had evolved into an astonishing array of forms, filling ecological niches from pole to pole. The late Cretaceous witnessed what paleontologists now recognize as peak diversity for several major dinosaur lineages. Hadrosaurs, ceratopsians, and ankylosaurs all experienced explosive radiations during this interval, particularly across the landmass known as Asia-America, which included Western North America and Eastern Asia. These weren't the lumbering giants of popular imagination, but highly specialized creatures adapted to specific environments with remarkable precision. Hadrosaurs, or duck-billed dinosaurs, dominated coastal wetlands with their sophisticated dental batteries capable of grinding tough vegetation. Some species sported elaborate cranial crests used for communication, visual displays and resonating chambers that likely filled ancient forests with haunting calls. Ceratopsians like Triceratops roamed northern biomes with their massive frilled skulls and horned faces, while their relatives displayed astonishing variety and ornamentation. The geographic distribution of these creatures reveals something unexpected. They were remarkably provincial despite their size and apparent mobility. Large, herbivorous dinosaurs exhibited persistent latitudinal and altitudinal zonation, with distinctive endemic associations confined to surprisingly small geographic ranges. Corythosaurus and Centrosaurus, the most abundant dinosaurs in southern Alberta during the Judithian stage, have never been found outside that region, despite their numerical dominance. Pentaceratops remains the only known Judithian ceratopsian from New Mexico. This stands in stark contrast to modern large mammals, whose ranges typically span much of a continent. Where modern mammal communities would share 11 to 16 species out of 20 across different latitudinal zones, late Cretaceous dinosaur communities showed far less overlap. The reasons likely involved highly specialized diets and narrow tolerances for environmental variation. Each species had carved out its niche with such efficiency that migration between ecosystems became unnecessary and perhaps impossible. North America's division by the Western Interior Seaway created distinct eastern and western biomes, but even within western Laramidia, northern and southern ecosystems developed markedly different character. Northern regions were dominated by Pachyrhinosaurs and Protoceratopsians, while southern areas hosted their own unique assemblages. By the Maastrichtian stage, the final chapter of the Cretaceous and the time period in which the asteroid impact occurred, most ecosystems had become dominated by single herbivore species. Triceratops reigned in the north, while the massive sauropod Alamosaurus held sway in southern regions. This faunal turnover coincided with the Laramide orogeny, a mountain-building event that uplifted the Central Rockies and caused dramatic drops in sea level, expanding North America's land area from 7.7 million square kilometers at the end of the Judithian to nearly 18 million square kilometers by the end of the Lancian, approaching the modern continental area. Carnivorous dinosaurs roamed these landscapes as apex predators, though they too showed patterns of distribution. Tyrannosaurus rex, perhaps the most famous dinosaur of all, stalked the northern regions of Laramidia during the final few million years of the Cretaceous. These enormous predators stretched up to 12 meters in length and possessed crushing bite forces unmatched in the terrestrial realm. Smaller theropods filled various predatory niches, and many of these displayed wider geographic ranges than their herbivorous prey, likely because they followed food sources across broader territories. The southern hemisphere hosted its own distinctive predators, abelisaurids, like Carnotaurus in South America and various other theropod lineages across Gondwanan continents, but dinosaurs alone didn't define this world. The oceans teemed with life in forms both familiar and utterly alien. Mosasaurs, massive marine reptiles descended from terrestrial lizards, ruled as oceanic apex predators, some species reaching lengths over 15 meters. Plesiosaurs, with their paddle-like limbs and elongated necks, hunted fish in shallow seas. Prehistoric sharks patrolled deeper waters. The Western Interior Seaway, that split North America, hosted rich marine ecosystems, preserved in fossil beds like Kansas's Niobrara chalk, where sharks, fish, marine reptiles, and diving birds left their remains in fine-grained sediments. Above these waters, pterosaurs, some with wingspans exceeding 10 meters, soared on thermal currents, the largest flying creatures ever to exist. The plant kingdom had undergone its own revolution. Angiosperms, flowering plants, had emerged earlier in the Cretaceous, and by the late Cretaceous were diversifying rapidly, beginning to challenge the long dominance of conifers, cycads, and ferns. This floral transformation provided new food sources and may have driven some of the herbivorous dinosaur diversification, though the exact relationship remains debated among paleontologists. Forests mixed ancient conifers with newer flowering trees. Ground cover included ferns, horsetails, and early flowering shrubs. The landscape was green and productive, a verdant world operating at maximum biological capacity. By any measure, life had never been more diverse or more widespread across Earth's surface. The biosphere hummed with evolutionary experimentation and ecological complexity. This was the world that existed on that spring morning 66 million years ago, thriving, diverse, utterly unprepared for the cosmic catastrophe bearing down from space. The Western Interior Seaway represents perhaps the most distinctive feature of late Cretaceous North America, a body of water that at its maximum extent stretched over 1,000 kilometers wide from the ancestral Rocky Mountains in the west to the Appalachian Highlands in the east. This was not a deep ocean basin, but a shallow epicontinental sea, reaching depths of perhaps only 800 to 900 meters at its deepest point. Two massive continental watersheds drained into it from both sides, diluting the marine waters and carrying enormous quantities of eroded sediment that formed shifting delta systems along low-lying coasts. The western boundary consisted of thick layers of sediment eroded eastward from the Sevier orogenic belt, making the western shoreline highly variable depending on fluctuations in sea level and sediment supply. The eastern shores, by contrast, experienced relatively little sedimentation. Water conditions within the seaway reveal a complex and sometimes hostile environment. Widespread carbonate deposition suggests the seaway maintained warm tropical temperatures with abundant calcareous planktonic algae thriving in the upper water column. Remnants of these deposits remain visible today in northwest Kansas, where Monument Rocks, exposed chalk formations, tower 70 feet over the surrounding rangeland, silent witnesses to ancient seas. The seaway functioned hydrologically much like a giant estuary, with riverine inputs exiting as coastal jets, while correspondingly drawing in water from the Tethys Ocean in the south and boreal waters flowing down from the north. This circulation pattern created dynamic water mass transport, but also contributed to environmental instability. During multiple periods throughout the late Cretaceous, the Western Interior Seaway experienced episodes of anoxia, intervals when bottom waters became completely devoid of oxygen, and the water column stratified into distinct layers. These oxygen-depleted conditions would have been lethal to most benthic organisms, restricting biodiversity and creating zones where only specially adapted creatures could survive. Studies examining concretionary faunas in the Pierre Shale of eastern Wyoming show clear relationships between diversity patterns and water depth. Samples with lower diversity and abundances correspond to intervals when water conditions were deepest and the paleo shoreline farthest west, while higher diversity matched periods when the paleo shoreline approached closer and shallow water conditions prevailed. The distribution of taxa and diversity most likely reflected migrating oxygen-controlled biofacies responding to variations in sea level and proximity to the western shoreline. Yet when conditions were favorable, life flourished spectacularly. The seaway hosted an impressive array of predatory marine reptiles, including various species of plesiosaurs and mosasaurs that hunted throughout the water column. Sharks prowled these waters in multiple forms: Squalicorax, the massive Cretoxyrina, and the giant Gyrophagus Tychodus mortoni, believed to have reached 10 meters in length. Advanced bony fish included Pachyrhizodus, Encodus, and the massive Xiphactinus, which grew 4 to 5 meters long, larger than any modern bony fish. These apex predators fed on rich populations of smaller fish, squid-like belemnites, and countless invertebrates including mollusks, ammonites, and planktonic organisms. The chalk formations that give the Cretaceous period its name originated from the accumulated platelets of coccolithophores, microscopic, planktonic algae that secreted calcium carbonate structures. These tiny organisms form the foundation of marine food webs, their billions of skeletons drifting down to the seafloor to create thick deposits of fine-grained limestone. Foraminiferans and radiolarians added their own contributions to the sedimentary record. On the muddy bottom, inoceramids, oyster-like bivalve mollusks, proved remarkably well adapted to life in oxygen-poor mud. These creatures left abundant fossils in the Kiowa, Greenhorn, Niobrara, Mancos, and Pierre formations, with great variety in shell forms allowing paleontologists to identify specific beds and date rock layers with precision. Most species fit easily in the palm of a hand, but giants like Inoceramus grandis could exceed a meter in diameter, their shells sometimes providing shelter for entire schools of fish. Above the water's surface, early birds shared the skies with pterosaurs. Hesperornis, a flightless diving bird with stout legs for swimming and tiny wings used for steering underwater rather than flight, pursued fish beneath the waves. The tern-like Ichthyornis, equipped with a toothy beak, represented a more recognizable avian form. These early birds coexisted with large pterosaurs, including Nyctosaurus and Pteranodon, the latter being extraordinarily common in the southern reaches of the seaway, and likely a major participant in surface ecosystem dynamics. The seaway was not merely a geographic feature, but a thriving biological system unto itself, a vast network of energy flow and nutrient cycling that connected terrestrial and marine realms in ways that shaped the entire continent. This interconnected world of land and sea, dinosaur and plesiosaur, forest and ocean, this was the reality on the morning the asteroid entered Earth's atmosphere. The object that would end the Mesozoic era began its existence not as a harbinger of doom, but as an unremarkable fragment of the early solar system, one among countless millions circling the Sun in the main asteroid belt between Mars and Jupiter. This belt, a vast ring of debris stretching from approximately 2.2 to 3.3 astronomical units from the Sun, represents the scattered remnants of a planet that never formed, its assembly prevented by Jupiter's overwhelming gravitational influence. For billions of years, these rocky bodies orbited in relative stability, occasionally colliding and fragmenting, but largely maintaining predictable paths through the void. The object that would become the Chicxulub impactor likely originated as part of a larger parent body, perhaps tens or even hundreds of kilometers across, before a collision shattered it into smaller pieces, sometime in the solar system's distant past. Scientists have worked backward from the impact itself to deduce the impactor's properties with remarkable precision. The asteroid measured approximately 10 to 15 kilometers in diameter, roughly 6 to 9 miles wide, making it large enough to cause global catastrophe, but small enough that Earth's gravitational well would accelerate it to devastating velocities. Its composition appears to have been carbonaceous chondrite, a primitive type of stony meteorite rich in carbon compounds and volatile materials, based on analysis of the impact debris layer and the chemical signatures preserved in the geological record. This composition distinguishes it from iron-nickel asteroids and suggests it formed in the outer regions of the asteroid belt, where temperatures remained cool enough for water ice and organic compounds to condense during the solar system's formation 4.6 billion years ago. The exact triggering event that sent this particular asteroid out of its stable orbit remains unknown, though several scenarios are plausible. A collision with another asteroid could have imparted sufficient momentum to alter its trajectory, nudging it into an orbital resonance with Jupiter. Gravitational sweet spots, where Jupiter's periodic tugging gradually amplifies changes in an object's orbit. Over hundreds of thousands or even millions of years, these resonances can pump up an asteroid's orbital eccentricity, stretching its path from a nearly circular orbit into an elongated ellipse that eventually crosses the orbit of Mars, then Earth. Alternatively, the Yarkovsky effect, subtle thermal forces created when an asteroid absorbs sunlight and re-radiates heat, could have slowly spiraled the object inward over immense timescales. Regardless of the mechanism, at some point the asteroid's path became unstable, and it began the long gravitational fall toward the inner solar system. By the time it crossed Mars's orbit, the asteroid had already been traveling for what could have been hundreds of thousands of years since its orbital disruption. Its velocity would have been governed by the laws of celestial mechanics that Kepler first described and Newton later explained. As it fell closer to the Sun, conservation of angular momentum demanded it accelerate. Crossing Earth's orbital distance, it would have been traveling at approximately 20 kilometers per second relative to the Sun, though its velocity relative to Earth would depend critically on the angle and direction of approach. Scientists calculate the impact velocity at roughly 20 to 40 kilometers per second. 45,000 miles per hour represents a reasonable middle estimate based on computer models of crater formation that match the observed dimensions and structure of the Chicxulub crater. The asteroid's trajectory brought it on a collision course with Earth at an angle estimated between 45 and 60 degrees from the horizontal, steep enough to deliver maximum destructive energy, but shallow enough to distribute ejecta over vast distances. Had it struck at a near vertical angle, much of the energy would have been directed downward into the crust with less material ejected into the atmosphere. Had it arrived at a very shallow angle, it might have skipped off the atmosphere like a stone across water, or fragmented higher in the atmosphere, distributing its energy over a wider area with less concentrated devastation. The actual angle proved catastrophically optimal, ensuring that a massive volume of vaporized rock would be injected into the upper atmosphere and beyond. beginning the global cascade that would darken skies worldwide. The evidence for these conclusions comes from multiple independent lines of investigation. The global layer of impact debris, known as the KPG boundary layer or KT boundary layer, contains elevated concentrations of iridium, an element rare in Earth's crust, but abundant in asteroids. This iridium anomaly, first discovered by physicist Luis Alvarez and his geologist son Walter Alvarez in 1980, provided the initial crucial clue that an extraterrestrial impact had occurred. Subsequent discoveries of shocked quartz grains, quartz crystals, bearing microscopic deformation patterns that only form under pressures exceeding 100,000 atmospheres, confirmed the impact hypothesis. As such, pressures occur naturally only during meteorite impacts or nuclear explosions. Further evidence comes from impact. Spherules, tiny glass beads formed when molten rock. Droplets were ejected into the atmosphere and solidified while airborne. These spherules have been found in sedimentary layers worldwide, their distribution patterns revealing information about ejection angles and velocities. The spherules near the impact site are larger and more abundant, while those found thousands of kilometers away are smaller and more uniformly distributed, consistent with global atmospheric transport of fine particles. Chemical analysis of these spherules shows they originated from both the asteroid itself and the target rocks at the impact site, providing a mixed signature that has allowed researchers to reconstruct both the impactor's composition and the geology of the impact location. The energy involved in this collision defies everyday comprehension. When the asteroid struck, it released approximately 100 teratons of TNT equivalent, that's 100 trillion tons, or about 4.2 x 1023 joules of energy. To put this in perspective, this represents more than 1 billion times the combined energy of the atomic bombs dropped on Hiroshima and Nagasaki, and roughly 4.5 billion times the explosive power of the Hiroshima bomb alone. Another way to conceptualize this magnitude: it equals approximately 10 billion times the energy of the largest thermonuclear weapon ever detonated. This was not merely an explosion, but a planetary scale catastrophe that would fundamentally alter Earth's climate and ecosystems within hours. The asteroid's approach trajectory can be inferred from the shape and structure of the Chicxulub crater itself. Detailed seismic surveys conducted across the Yucatan Peninsula have revealed that the crater measures approximately 200 kilometers in diameter, making it the second largest confirmed impact structure on Earth. The crater displays an asymmetric shape that indicates the asteroid struck at an oblique angle rather than straight down. This obliquity proved crucial to the magnitude of the disaster. Computer simulations show that an impact angle between 45 and 60 degrees from horizontal would maximize the volume of material ejected into the atmosphere, while still delivering catastrophic ground shock. A more vertical impact would have driven energy deeper into the crust with less atmospheric injection. A shallower angle might have caused the asteroid to skip or fragment higher up, distributing its energy over a larger area with less concentrated devastation. The target site contributed significantly to the catastrophe's severity. The asteroid struck in what was then a shallow tropical sea, overlying a thick sequence of sedimentary rocks, including massive deposits of gypsum and anhydrite, minerals rich in sulfur compounds. When the impact vaporized these sulfur-bearing rocks along with limestone containing calcium carbonate, it injected enormous quantities of sulfur dioxide and carbon dioxide directly into the stratosphere. Scientists estimate that several thousand gigatons of material, asteroidal fragments, vaporized rock, sulfates, and water vapor were ejected at velocities exceeding 5 kilometers per second. Some of this material achieved escape velocity, exceeding 11 kilometers per second, and was permanently lost to space, while the remainder began its deadly reign back to Earth. The returning ejector interacted violently with Earth's atmosphere. High-velocity rock fragments and droplets of molten material created a fast-moving cloud that circumnavigated the globe within approximately 4 to 5 hours of impact, carrying dust, soot, sulfate aerosols, and solid debris. This cloud formed through complex interactions between ballistic ejector and atmospheric gases, creating thermal radiation intense enough to ignite vegetation across vast distances. Evidence suggests that wildfires engulfed an estimated 70% of the planet's forests, adding massive quantities of soot to the already particle-laden atmosphere. The combination of impact dust, sulfate aerosols, and wildfire soot would reduce sunlight reaching Earth's surface by more than 50%, initiating what researchers term an impact winter, a period of global darkness and cold that climate models suggest persisted for months to years, possibly as long as a decade. The geological record preserves this moment with remarkable clarity. At dozens of locations worldwide, a thin clay layer marks the boundary between Cretaceous rocks below and Paleogene rocks above, the famous KPG boundary, dated with precision to 66.0 million years ago. This boundary layer, sometimes only a few centimeters thick, contains the concentrated debris of global catastrophe, elevated iridium, shocked quartz, impact spherules, and in some locations, a charcoal layer documenting widespread fires. In New Jersey, 2,500 kilometers from the impact site, paleontologists found fossil evidence for instantaneous extinction of diverse animals in a soil layer just 10 centimeters thick, indicating that death and burial occurred suddenly across wide distances. The asteroid had crossed millions of kilometers of empty space to arrive at this precise location at this precise moment, and in doing so, it sealed the fate of Earth's dominant life forms. The mechanics of orbital dynamics dictate that objects falling toward the inner solar system from the asteroid belt follow predictable mathematical paths, though chaos theory ensures that tiny perturbations can produce vastly different outcomes over millions of years. The Chicxulub impactor's trajectory was set by gravitational interactions that had been accumulating for potentially hundreds of thousands of years before the final approach. Jupiter's massive gravitational field dominates the asteroid belt, creating resonance regions where orbital periods achieve simple fractional relationships with Jupiter's own orbit. A 3.1 resonance, for instance, means an asteroid completes 3 orbits for every one Jupiter completes. These resonances act as gravitational whirlpools, gradually pumping up orbital eccentricity until an asteroid's path becomes unstable and intersects the orbits of inner planets. Once the asteroid crossed into Earth-crossing orbit, the final encounter became merely a matter of timing. Earth travels through space at approximately 30 kilometers per second in its orbit around the Sun, covering its own diameter in roughly 7 minutes. The asteroid would have approached on its own independent trajectory, and the collision occurred because both objects arrived at the same point in space at the same instant. A cosmic coincidence with catastrophic consequences. Had Earth been merely a few minutes earlier or later in its orbital position, the asteroid would have missed entirely, passing harmlessly through the space our planet had just vacated or had yet to reach. The dinosaurs would have continued their reign, and the evolutionary path that eventually produced humans might never have occurred. The impact site itself was selected by pure chance, yet its characteristics profoundly influenced the severity of the extinction event. The asteroid struck in what was then a shallow tropical sea approximately 100 meters deep, overlying thick sequences of sedimentary rocks that included massive deposits of anhydrite and gypsum, calcium sulfate minerals formed from ancient evaporated seabeds. When the impact vaporized these sulfur-rich rocks, it injected an estimated several hundred gigatons of sulfur dioxide directly into the stratosphere. This sulfur dioxide rapidly combined with water vapor to form sulfate aerosols, tiny droplets of sulfuric acid suspended in the upper atmosphere. These aerosols had a dual effect on Earth's radiation budget. They heated the stratosphere by absorbing incoming solar radiation while simultaneously cooling Earth's surface by reflecting sunlight back to space before it could warm the ground. The long-term consequences unfolded in phases, each with distinct characteristics documented in the geological record. Immediately following impact, returning debris created a series of temperature spikes as vaporized material rained back through the atmosphere, generating enough thermal radiation to ignite vegetation across vast regions. An estimated 70% of Earth's forests burned in the hours and days following impact, adding enormous quantities of soot to an atmosphere already laden with dust and sulfate aerosols. This initial phase of extreme heat gave way rapidly to what researchers term impact winter, a period of profound cooling caused by the atmospheric particle load blocking sunlight. Temperatures would have plummeted below pre-impact conditions, creating freezing conditions even in tropical regions. This cold phase persisted for months to possibly years as dust remained suspended in the atmosphere. When the dust finally settled and sulfate aerosols were washed out as acid rain, the climate swung in the opposite direction. The massive quantities of carbon dioxide released by vaporizing limestone several hundred billion tons injected into the atmosphere within minutes created greenhouse warming that persisted far longer than the initial cooling. Recent research examining fossilized marine organisms has revealed that global temperatures increased by approximately 5 degrees Celsius, and this warming spell endured for roughly 100,000 years. Some climate models suggest greenhouse warming may have persisted for thousands of years, fundamentally altering Earth's climate system on timescales far exceeding the initial catastrophe. This trajectory through space, this 6-mile wide chunk of carbonaceous rock traveling at 45,000 miles per hour, carried within its momentum the end of an era. The energy it would release upon collision equaled approximately 10 billion times the most powerful thermonuclear weapon humans have ever built. The asteroid had no consciousness, no intent, no awareness of the destruction it would cause. It simply followed the laws of physics, its path determined by gravitational forces acting across millions of years and millions of miles. And on one spring morning 66 million years ago, that path intersected Earth's at precisely the wrong place and precisely the wrong time. The sun rose over the late Cretaceous landscape on what appeared to be an ordinary spring morning approximately 66 million years ago. Research analyzing fossilized fish bones from the Tsunamis site in North Dakota, located roughly 3,000 kilometers from the impact zone, has revealed that the asteroid struck during the Northern Hemisphere spring, based on growth patterns preserved in paddlefish and sturgeon bones that record seasonal variations like tree rings. This timing meant that many species were in the midst of breeding seasons, nesting behaviors, and the renewed growth cycles that characterize the warmer months in temperate latitudes. The world was alive with activity, ecosystems operating at full capacity after the dormancy of winter, completely unaware that within hours, everything would change forever. Across the western landmass of Laramidia, Triceratops herds moved through coastal lowlands and river valleys, their massive 3-horned skulls lowered to crop vegetation with powerful beaked jaws. These ceratopsians, among the last and largest of their lineage, had become the dominant megaherbivores across northern regions during the final million years of the Cretaceous. Individual adults weighed between 6 and 12 metric tons and measured up to 9 meters in length, making them formidable presences in any ecosystem. Their elaborate bony frills, often spanning more than 2 meters across, served multiple functions: displays for attracting mates, thermoregulation by increasing surface area for heat dissipation, and possibly defense or species recognition. Fossil evidence suggests Triceratops exhibited some degree of social behavior, with bonebed discoveries containing multiple individuals of varying ages, though whether they formed permanent herds or temporary aggregations remains debated among paleontologists. The plant life these herbivores consumed had diversified dramatically during the late Cretaceous. Angiosperms, flowering plants, had emerged earlier in the period and by 66 million years ago were competing successfully with conifers, cycads and ferns for dominance across many ecosystems. This floral revolution may have driven some of the herbivorous dinosaur diversification observed in the fossil record, as new food sources with different nutritional profiles became available. Triceratops possessed sophisticated dental batteries capable of processing tough vegetation, and where patterns on fossilized teeth suggest diets that included palms, cycads, and possibly the tougher fronds of ferns. The landscape they inhabited was a mosaic of habitats: river floodplains lined with riparian forests, open woodlands of conifers mixed with flowering trees, and coastal plains where sea breezes carried the salt tang of nearby oceans. Predators moved through these same landscapes with calculated stealth. Tyrannosaurus rex, the apex predator of northern Laramidia, stalked prey across territories that likely spanned dozens of square kilometers. These massive theropods stood approximately 4 meters tall at the hips and stretched 12 meters from snout to tail tip. With adults weighing between 8 and 14 metric tons, depending on sex and individual variation. Their skulls alone measured up to 1.5 meters in length, housing teeth that could exert bite forces exceeding 57,000 newtons, the most powerful bite of any terrestrial animal ever documented. These were not the sluggish scavengers once portrayed in outdated reconstructions, but active hunters capable of running speeds, estimated between 17 and 40 kilometers per hour based on biomechanical modeling of their leg, proportions and body mass. The fossil record provides glimpses into Tyrannosaurus hunting behavior through preserved pathologies and healed injuries. Examination of Triceratops bones has revealed tooth marks matching Tyrannosaurus dentition, with some showing signs of healing, indicating the prey animal survived the initial attack. Other specimens display evidence of successful kills, bones broken and gnawed, with tooth marks penetrating deep into the bone cortex in patterns consistent with flesh stripping and bone crushing. On this particular spring morning, any number of such encounters were likely unfolding across the landscape as predators sought prey and herbivores attempted to avoid becoming meals. The dynamic equilibrium between hunter and hunted had been refined over millions of years of coevolution, each side adapting strategies and counter-strategies in an endless arms race that would be abruptly terminated by the approaching catastrophe. Smaller dinosaurs filled countless ecological niches across this landscape. Hadrosaurs, duck-billed dinosaurs, congregated near wetlands and river systems where their grinding teeth could process aquatic vegetation and riparian plants. Some species possessed elaborate cranial crests that functioned as resonating chambers, potentially producing distinctive calls used for communication within herds, territory defense, or mate attraction. Fossil trackways preserve evidence of hadrosaur social behavior, showing groups moving together and suggesting coordinated herd dynamics similar to those observed in modern large herbivores. Ankylosaurs, heavily armored dinosaurs with backs covered in osteoderms and tails tipped with massive bony clubs, browsed low-growing vegetation in more open habitats, their defensive adaptations making them virtually immune to predation except by the largest carnivores. Above these terrestrial landscapes, pterosaurs soared on thermal currents generated by the warming spring air. Pteranodon and other large flying reptiles patrolled coastlines and inland seas, their toothless beaks adapted for catching fish from surface waters. These creatures represented the culmination of millions of years of pterosaur evolution, with some species achieving wingspans exceeding 10 meters, making them the largest flying organisms ever to exist. Recent biomechanical studies suggest these giants relied on dynamic soaring techniques similar to modern albatrosses, exploiting wind gradients over water surfaces to achieve efficient long-distance flight with minimal energy expenditure. On this particular morning, countless pterosaurs likely wheeled above the western interior seaway and coastal waters, scanning for schools of fish moving near the surface as they had done for millennia. The debate over whether dinosaur diversity was declining or stable immediately before the extinction has occupied paleontologists for decades, and fossil evidence provides somewhat contradictory signals depending on analytical methods. Some studies examining the fossil record suggest dinosaur diversity peaked during the Campanian stage, approximately 75 to 72 million years ago, and then declined through the final Maastrichtian stage leading up to the extinction event. These analyses indicate that net diversification rates became negative around 76 million years ago due to increasing extinction rates that exceeded speciation rates, with herbivorous dinosaurs experiencing a particularly marked decline. The pattern suggests that long-term environmental changes, including global climate cooling and the retreat of shallow seas, may have stressed dinosaur populations for millions of years before the impact. However, other research using different statistical approaches reaches opposite conclusions. Studies employing rarefaction techniques and abundance-based coverage estimators found no evidence for a decline in dinosaur diversity near the end of the Cretaceous, suggesting instead that apparent decreases reflect sampling bias rather than true biological patterns. These analyses estimate that the Campanian and Maastrichtian stages had essentially equivalent dinosaur diversity, approximately 246 genera each, with the Maastrichtian record being less complete at only 39% compared to the Campanian's 48% completeness. The presence of the largest members of several major lineages, Tyrannosaurus, Ankylosaurus, Triceratops, in the latest Maastrichtian rocks suggests food remained plentiful and ecosystems functioned normally immediately before extinction. A study of fossil sites in the Catalan Pyrenees found high dinosaur diversity persisting until the asteroid impact, with more than 100 species present in that region alone. The truth likely incorporates elements of both perspectives. Regional variation almost certainly existed, with some areas experiencing diversity declines, while others maintained stable or even increasing species richness. The Hell Creek Formation of Montana, the most extensively studied late Maastrichtian dinosaur-bearing formation, shows evidence of large, thriving populations right up to the KPG boundary, But this represents only a small geographic area covering part of one continent. Recent estimates suggest that between 628 and 1,078 non-avian dinosaur species existed globally at the time of the extinction, a substantial diversity that would be obliterated in a geological instant. Whatever the precise trajectory of diversity trends, the fossil record demonstrates unequivocally that diverse dinosaur communities occupied ecosystems across multiple continents on that spring morning 66 million years ago beneath the waves of the western interior, seaway and in oceans worldwide. Marine ecosystems teemed with complex food webs. Mosasaurs, the ocean's apex predators, patrolled open waters, hunting large fish, sharks, sea turtles, and even other marine reptiles. The massive Tylosaurus and Mosasaurus reached lengths over 15 meters, their powerful tails propelling them through the water with deadly efficiency. Plesiosaurs, with their distinctive long necks and paddle-like limbs, hunted in shallower coastal waters, using their flexible necks to strike at prey with surprising speed despite their seemingly cumbersome body plans. These marine reptiles had no evolutionary precedent among modern animals. They represented unique solutions to the challenges of aquatic life, and their lineages would be entirely erased by the coming catastrophe. Fish populations formed the foundation of marine food webs. Schools of smaller species congregated near coastlines and river mouths where nutrient-rich freshwater mixed with marine systems, creating highly productive zones that attracted predators throughout the food chain. The giant predatory fish Xiphactinus, growing 4 to 5 meters long, hunted these schools. Specimens preserved with smaller fish still in their stomachs providing direct evidence of predator-prey relationships. Sharks of multiple lineages patrolled deeper waters, including the massive Cretoxyrhina and the Durophagus Tychodus mortoni, which may have reached 10 meters in length. On that morning, countless such predators pursued their prey through waters that would soon be disrupted by unimaginable violence. The spring timing of the impact meant many species were particularly vulnerable. In the northern hemisphere, breeding seasons were underway or about to begin. Nests would have contained eggs or young offspring. Migrations patterns were in flux. Energy reserves depleted by winter would not yet have been fully replenished. The fossil evidence from the Tanis site, where paddlefish and sturgeon died instantly when the impact occurred, preserves this moment with extraordinary clarity. The growth rings in their bones literally frozen at the spring growth phase. This was life as usual on a planet that had operated under consistent rules for millions of years, rules that were about to be rewritten in a single, devastating hour. Beneath the canopy of coniferous forests, and among the understory of ferns and flowering shrubs, small mammals moved with cautious efficiency through a world dominated by giants. These creatures, distant ancestors of the mammals that would eventually inherit the planet, occupied marginal ecological niches as nocturnal insectivores, seed-eaters, and opportunistic omnivores. Most were roughly the size of modern shrews or rats, with a few exceptional species reaching dimensions comparable to small cats. Fossil evidence suggests they possessed relatively large brains for their body size, acute senses adapted for low-light conditions, and fur coats that provided insulation during cool nights. Their metabolic strategies differed fundamentally from the dominant reptilian megafauna. These mammals maintained constant body temperatures through internal heat generation, allowing activity across a wider range of environmental conditions but demanding nearly constant food intake to fuel their energetic lifestyles. The fossil record from the Hell Creek Formation and other late Maastrichtian deposits preserves evidence of at least a dozen mammal species coexisting with dinosaurs in the final million years before extinction. Multituberculates, an extinct group characterized by specialized teeth with multiple cusps, had diversified into numerous ecological roles, some arboreal and others terrestrial. Metatherians, relatives of modern marsupials, scavenged and hunted insects across forest floors. Eutherians, the lineage that would eventually give rise to placental mammals, including humans, existed as small generalists exploiting whatever food sources they could access, without competing directly with dinosaurs. On that spring morning, these mammals likely emerged from burrows and tree hollows as dusk approached, preparing for another night of foraging in the shadows, cast by creatures hundreds of times their size. Insects swarmed in enormous numbers across every habitat. Beetles, flies, primitive wasps, and early butterflies pollinated the expanding diversity of flowering plants. Dragonflies, some with wingspans approaching those of modern birds, hunted smaller flying insects above wetlands. Termites and wood-boring beetles broke down dead vegetation, recycling nutrients back into the soil. Ants had already evolved into social colonies, their underground cities housing thousands of individuals, organized into complex caste systems. The coevolution between insects and angiosperms had been accelerating for tens of millions of years, with plant species developing sophisticated strategies to attract pollinators through color, scent, and nectar rewards, while insects evolved increasingly specialized morphologies to exploit these resources. This mutualistic relationship powered much of the ecosystem's productivity, and on that morning, countless such interactions were occurring across the landscape. Bees visiting flowers, beetles consuming pollen, butterflies probing nectar sources with long proboscises. The atmosphere itself carried different qualities than the air of the modern world. If oxygen levels indeed reached 25 to 35%, as some amber studies suggest, though this remains debated, the air would have been noticeably richer, potentially capable of supporting more intense wildfires and enabling insects to achieve larger body sizes than currently possible. The higher oxygen concentration might have made breathing feel effortless, like standing at sea level after descending from altitude. Carbon dioxide levels hovering around 300 to 650 parts per million created greenhouse conditions that kept global temperatures elevated and prevented polar ice formation. The sky itself might have appeared subtly different, perhaps a slightly deeper blue due to atmospheric composition variations, with cloud patterns reflecting the altered circulation patterns of a warmer world with no ice caps to disrupt. Atmospheric flow, weather systems on that spring morning would have been governed by the same physical principles that control modern climate, but operating within different boundary conditions. Without polar temperature gradients to drive jet streams, atmospheric circulation patterns would have been more zonal and less dynamic than today's weather. Tropical cyclones might have formed at higher latitudes, drawing energy from warm ocean waters that extended much farther toward the poles. The western interior seaway would have generated its own localized weather patterns as temperature differentials between land and water drove sea breezes and land breezes in daily cycles. Thunderstorms likely developed along the seaways, coasts each afternoon as rising thermal currents over sun-heated land collided with cooler, maritime air masses. Rivers flowing from the ancestral Rocky Mountains carried snowmelt and rainfall toward both the western interior seaway and the distant Pacific Ocean, their floodplains supporting rich riparian ecosystems. These waterways teemed with fish, ancient relatives of modern sturgeon, gar, and bowfin, along with freshwater turtles, crocodilians, and amphibians. The river systems served as corridors connecting different habitats, allowing genetic exchange between populations and providing migration routes for species tracking seasonal resources. Along riverbanks, tracks and trails documented the constant movement of dinosaurs coming to drink, predators ambushing prey at water's edge, and the smaller creatures that lived their entire lives within meters of flowing water. This was the world in its final hour of normalcy, a functioning, thriving biosphere, operating according to rules established over hundreds of millions of years of evolution. Energy flowed from sunlight through photosynthesis into plant tissues, then through herbivores into carnivores, and finally into decomposers that returned nutrients to the soil. Predator and prey populations maintained dynamic equilibrium. Species competed and cooperated. Young were born, adults died, and the cycle continued as it had for eons. Nothing in the behavior of any creature suggested the coming catastrophe. The asteroid was already slicing through the upper atmosphere, its passage beginning to generate the first faint atmospheric disturbances. But on the ground, life proceeded exactly as it had the day before, and would have the day after, if that day had been allowed to arrive. 59 minutes before impact, the asteroid was approximately 107,000 kilometers from Earth's surface, roughly halfway to the Moon, and closing the distance at approximately 20 to 40 kilometers per second. At this range, the object would have been completely invisible to any observer on Earth's surface, appearing as nothing more than a dim point of light indistinguishable from countless other celestial objects populating the sky. Had dinosaurs possessed astronomical instruments comparable to modern amateur telescopes, they might have detected the approaching body as a slowly moving dot against the stellar background. But its significance would remain utterly unclear until the final minutes. The asteroid traveled through the vacuum of space in complete silence, its surface temperature governed solely by solar radiation, blistering hot on the sun-facing hemisphere. frigid on the shadow side, with no atmosphere to moderate the extremes. The physics of atmospheric entry dictate that significant interactions between a celestial object and Earth's atmosphere begin at altitudes between 100 and 120 kilometers, the conventional boundary known as the Kármán line, where atmospheric density becomes sufficient to affect objects traveling at orbital velocities. For the Chicxulub impactor, traveling at speeds potentially exceeding 30 kilometers per second, this threshold would be crossed in less than 4 seconds once the asteroid reached the upper atmosphere. At 59 minutes before impact, the object was still moving through near-perfect vacuum, where individual air molecules were so sparse that collisions with the asteroid's surface occurred only sporadically. The laws of celestial mechanics governed its motion completely, with Earth's gravitational field steadily accelerating the object inward along its predetermined trajectory. Earth's gravitational acceleration at the distance of the Moon is approximately 0.0027 meters per second squared, barely perceptible, but it increases with the inverse square of distance, meaning that as the asteroid fell closer, the gravitational pull strengthened exponentially. By the time the object reached positions equivalent to geosynchronous satellite orbits, roughly 36,000 kilometers altitude, Earth's gravity had grown nearly 30 times stronger than at lunar distance. This accelerating inward fall represented the final stage of a journey that may have begun millions of years earlier, when the asteroid's orbit was first perturbed out of the main belt. Every second brought it 30 to 40 kilometers closer to collision, and with each passing moment, Earth's gravitational well tightened its grip, making escape or deflection increasingly impossible. The asteroid's composition, primarily carbonaceous chondrite material, meant its surface likely appeared dark grey to black, with a rough, irregular texture created by billions of years of micrometeorite impacts and thermal cycling. Unlike the smoothly cratered surfaces of larger bodies with sufficient gravity to achieve hydrostatic equilibrium, this 6-mile-wide fragment would have retained its angular, fractured appearance from whatever collision originally liberated it from a larger parent body. Surface features might have included impact craters from smaller collisions, grooves and ridges marking internal structural weaknesses, and possibly regions of different albedo indicating compositional variations within the ancient rock. As the object tumbled through space, most asteroids rotate with periods ranging from hours to days. Different faces would alternately bask in sunlight or freeze in darkness, though this thermal cycling would cease to matter once atmospheric friction began heating the entire mass to incandescent temperatures. At distances beyond several hundred kilometers, Earth still appeared relatively small in the asteroid's sky, a blue and white disk perhaps 10 to 20 times the apparent diameter of the Moon as seen from Earth. But the planet was growing visibly larger, with each passing minute, its features resolving into greater detail as the separation narrowed. The asteroid approached from a trajectory angled between 45 and 60 degrees from horizontal, a path that would bring it screaming in from the southeast, crossing the Gulf of Mexico toward the Yucatan Peninsula. From the asteroid's perspective, Earth no longer represented just another planetary body among many in the solar system, but had become the dominant object filling more and more of the visible sky, its gravitational field an inescapable trap pulling the rock inexorably toward collision. The energy contained in the asteroid's motion was almost inconceivable. Kinetic energy scales with the square of velocity, meaning that doubling the speed quadruples the energy. At 30 kilometers per second, a reasonable mid-range estimate, the asteroid carried approximately 4.2 x 1023 joules of kinetic energy, equivalent to roughly 100 million megatons of TNT. This represented more energy than all the world's nuclear arsenals combined could release if detonated simultaneously, concentrated into a single 6-mile-wide projectile. Every second of continued flight brought this enormous energy reservoir closer to its inevitable release point, where in a fraction of a second, all that kinetic energy would be converted into heat, shock waves, and the violent displacement of crustal material on a scale unprecedented in millions of years of Earth history. On Earth's surface, no creature possessed any awareness of the approaching object. The asteroid remained far too distant and too small to resolve against the daytime sky, lost in the glare of sunlight. Even during nighttime hours in previous days, its faint reflected light would have been indistinguishable from the countless stars visible in an unpolluted late Cretaceous sky. The laws of orbital mechanics that governed its inward fall operated on scales utterly beyond the perception of terrestrial life. Dinosaurs continued their daily activities, feeding, hunting, socializing, resting, completely oblivious to the countdown that had begun. The vacuum through which the asteroid traveled carried no medium for sound propagation. The rock moved in absolute silence, its passage marked only by the gravitational perturbations it induced in nearby space. Had any spacecraft been positioned to observe from a distance, the scene would have appeared almost serene, a dark, irregular object falling steadily toward the blue and white sphere of Earth, sunlight glinting off its rough surface as rotation brought different facets into illumination. But there were no observers, no witnesses to this cosmic dance reaching its final stages. The asteroid and Earth simply moved along their mathematically determined paths through space, and those paths were converging with absolute inevitability. At 59 minutes before impact, the asteroid had already passed the point where any realistic intervention could have altered the outcome. Even if advanced technology existed to detect the threat, changing the trajectory of a 6-mile-wide object traveling at 30 kilometers per second would require forces beyond imagination. Nuclear explosions detonated against its surface might fragment it but wouldn't significantly alter the momentum of the resulting debris cloud. Millions of smaller impacts might arguably cause even more widespread devastation than a single, concentrated strike. Gravitational deflection using spacecraft would demand decades of continuous thrust to accumulate meaningful trajectory changes. At less than 1 hour from collision, the asteroid's fate and Earth's were inseparably linked. The object's internal structure, formed billions of years earlier, during the solar system's formation, contained within it the frozen record of ancient processes. Carbonaceous chondrites represent some of the most primitive materials in the solar system, chemical compositions virtually unchanged since the pre-solar nebula collapsed to form the Sun and planets. The asteroid likely contained grains that predated the Sun itself. Microscopic diamonds and silicon carbide crystals formed in the atmospheres of dying stars that existed before the solar system coalesced. In a sense, this rock carried within its matrix the ashes of earlier stellar generations, and it was about to deliver this ancient stellar material to Earth's surface. In the most violent manner imaginable, the approach trajectory brought the asteroid across the plane of Earth's orbit at an angle, calculated to maximize atmospheric injection of vaporized material. Had the impact angle been more vertical, approaching 90 degrees from horizontal, much of the energy would have been driven downward into the crust, creating an even deeper crater but ejecting less material into the atmosphere. Had the angle been shallower than 30 degrees, the asteroid might have fragmented higher in the atmosphere or potentially skipped off the upper atmospheric layers like a stone across water, its energy distributed over a much wider area. The actual angle between 45 and 60 degrees represented a catastrophic optimum, steep enough to penetrate completely to the surface, shallow enough to maximize the volume of vaporized target rock blasted upward and outward into the atmosphere and beyond. Computer simulations reconstructing the impact have revealed that the asteroid would vaporize approximately 100 times its own mass in target rock, creating a fireball of superheated plasma that would expand to engulf thousands of cubic kilometers within seconds. The impact would generate temperatures exceeding 10,000 degrees Celsius, hot enough to vaporize rock instantaneously and create a plasma state where atomic nuclei and electrons separate. This plasma would radiate thermal energy in all directions, and the returning ejector would heat the atmosphere globally to temperatures capable of igniting vegetation across vast distances. The asteroid carried within its kinetic energy the capacity to fundamentally alter Earth's climate for years or decades, all concentrated into a single 6-mile-wide package. The shallow sea above the impact site, approximately 100 meters deep, would provide essentially zero protection. Water possesses high heat capacity and density, but at the velocities and energies involved, the ocean would be swept aside and vaporized in the first microseconds of contact, adding enormous quantities of superheated steam to the expanding fireball. The asteroid would punch through the water column and into the underlying sedimentary rocks without meaningful deceleration, transferring its momentum directly into the crust. The vaporization of seawater would add yet another destructive component to the global catastrophe. Water vapor is itself a potent greenhouse gas, and the immense quantities injected into the stratosphere would contribute to post-impact climate disruption. At 59 minutes before impact, all these consequences remained locked in the future, their inevitability determined by physics, but their reality not yet manifest. The asteroid continued its silent fall through vacuum, and on Earth below, life proceeded in complete ignorance of the approaching doom. The gravitational forces acting on the asteroid increased exponentially as distance decreased, following Newton's inverse square law with mathematical precision. At this stage of approach, Earth's gravity dominated all other influences. The Sun's gravitational pull, Jupiter's distant tug, even the faint pressure of solar radiation striking the asteroid's surface, all became negligible compared to the accelerating inward pull of the planet directly ahead. The trajectory had become fixed and inevitable, locked into a collision path that no natural force could now alter. Every calculation of orbital mechanics, every equation describing ballistic motion through space, pointed toward the same conclusion. Impact would occur in less than 1 hour. The asteroid's rotation continued as it had for billions of years, though this spin would become irrelevant within the hour. Whether the object completed one rotation every few hours or every few days made no difference to the outcome. The angular momentum would be utterly overwhelmed by the linear momentum of the 30 km/s velocity at impact. The rock tumbled through space following whatever rotational state had been imparted by its last significant collision, perhaps millions of years earlier. Different phases alternated between sunlight and shadow, surface temperatures cycling between extremes, but within minutes, atmospheric friction would heat the entire mass to incandescence, erasing these thermal variations in a uniform glow of destruction. The distance to Earth's surface, still approximately 177,000 kilometers at the 59-minute mark, represented roughly 46% of the distance to the Moon. This separation would close at rates increasing with each passing second as gravitational acceleration added velocity to the asteroid's already tremendous speed. Within 30 minutes, the distance would be halved. Within 50 minutes, only tens of thousands of kilometers would remain. During the final 10 minutes, the visible size of Earth in the asteroid's sky would balloon dramatically as the distance collapsed from tens of thousands of kilometers to mere hundreds, then to zero. The energy equation remained brutally simple. Kinetic energy equals 1/2 mass times velocity squared. With mass fixed at approximately 1.0 to 2.5 x 10^15 kilograms, roughly 1 to 2.5 trillion metric tons, and velocity around 30 kilometers per second, the resulting kinetic energy approached 4.2 x 10^23 joules. This represented the explosive equivalent of 100 million megatons of TNT, or approximately 10 billion times the energy released by the atomic bomb dropped on Hiroshima. All of this energy was currently stored as motion. The asteroid's tremendous velocity through space. Within 1 hour, that motion would be arrested in a fraction of a second, and all that kinetic energy would be converted instantaneously into other forms: heat, shock waves, seismic energy, and the violent displacement of crustal. Material.computer models simulating the impact have revealed that the first microsecond of contact would see pressures at the impact interface exceed several hundred gigapascals, millions of times atmospheric pressure. These pressures would instantaneously vaporize both the asteroid and the upper layers of target rock, creating a plasma fireball with temperatures exceeding 10,000 degrees Celsius. The shock wave would propagate through the crust at velocities exceeding the speed of sound in rock, fracturing and displacing material for hundreds of kilometers in all directions. Within the first second after contact, a crater 30 kilometers wide would have already formed, and the excavation would continue for minutes as rebounding crustal material created the final 200-kilometer diameter structure. At 59 minutes before this catastrophe, the asteroid continued its silent fall through vacuum, and on Earth below, the spring morning proceeded without interruption. Pterosaurs wheeled above the western interior seaway, scanning for fish. Triceratops herds moved through coastal lowlands, cropping vegetation. Tyrannosaurus stalked prey through riparian forests. Small mammals prepared to retreat to burrows as daylight brightened. Marine reptiles hunted in warm, shallow seas. Insects pollinated flowers. Bacteria processed nutrients in soil. The entire planetary ecosystem operated according to patterns refined over hundreds of millions of years of evolution. None of these creatures possessed any mechanism to detect the approaching threat. Even if some theoretical sense could have perceived the asteroid's presence, no instinct existed to interpret the information or trigger avoidance behavior. The concept of an asteroid impact lay entirely outside the evolutionary experience of every terrestrial species. Life had adapted to countless challenges: predation, disease, climate variation, volcanic eruptions, sea level changes, but not to objects falling from space at cosmic velocities. The approaching rock represented something fundamentally beyond the scope of adaptation, a threat operating on timescales measured in minutes rather than generations, delivering consequences that no evolutionary strategy could mitigate. The 59 minutes remaining before impact represented a cosmic countdown utterly disconnected from the biological rhythms governing life on Earth's surface. While the asteroid fell steadily closer, following the inexorable mathematics of gravitational attraction, creatures below continued patterns of behavior shaped by 4 billion years of evolution. Feeding, reproducing, competing, cooperating, all of it about to become irrelevant. At 30 minutes before impact, the asteroid had crossed into the space between Earth and the Moon, now approximately 90,000 kilometers from the surface and closing at velocities approaching 30 kilometers per second. Earth no longer appeared as a distant disk, but dominated the entire forward view. A vast sphere of blue oceans, white clouds, and brown-green landmasses filling the asteroid's sky. The object continued its silent fall through near vacuum, though it was now entering regions where Earth's upper atmosphere began to assert itself in barely perceptible ways. At these altitudes, atmospheric density remained incredibly low, only a few atoms per cubic centimeter, but the asteroid's tremendous velocity meant that even these sparse molecules would soon begin interacting with its surface. The physics of atmospheric entry are governed by energy transfer equations that become increasingly violent as velocity and atmospheric density increase. At 30 kilometers per second, each collision between an air molecule and the asteroid's surface released kinetic energy as heat. At 90,000 kilometers altitude, these collisions remained rare. The space between Earth and its satellites is not true vacuum, but rather an extremely tenuous extension of the atmosphere. Individual atoms of hydrogen and helium, along with ionized particles trapped in Earth's magnetosphere, occasionally struck the asteroid's leading surface. Each impact converted a tiny fraction of kinetic energy into thermal energy, but at this stage, the heating remained negligible. The target zone, the Yucatan Peninsula and surrounding Gulf of Mexico, was now directly visible along the asteroid's approach vector. The shallow tropical sea covering what would become the impact site reflected sunlight in patterns modulated by wind-driven waves and deep water currents. The limestone platform and overlying sedimentary rocks that would be vaporized within half an hour showed no indication of their imminent destruction. The water depth at the future impact site measured approximately 100 to 650 meters, depending on the exact strike point within what would become the crater's boundaries. Beneath the seafloor, kilometers of sedimentary rocks, primarily limestone, dolomite, and anhydrite, rested atop 35 kilometers of continental crust. All of this geological structure was about to be fundamentally reorganized in a matter of seconds. At 30 minutes to impact, the asteroid had fallen far enough into Earth's gravitational well that its velocity relative to the surface was now substantially higher than its original heliocentric orbit velocity. Earth's gravity had accelerated the object continuously throughout its approach, adding kilometers per second to its already tremendous speed. The impact velocity would reach approximately 20 kilometers per second based on crater modeling, roughly 45,000 miles per hour, striking at an oblique angle between 45 and 60 degrees from horizontal, approaching from the northeast. This angle would prove catastrophically efficient at maximizing atmospheric injection of vaporized material while delivering full kinetic energy to the surface. Computer simulations reconstructing these final minutes have revealed the cascade of physical processes about to unfold. As the asteroid penetrated deeper into Earth's atmospheric envelope, the rate of molecular collisions would increase exponentially. At altitudes below 120 kilometers, the conventional edge of space known as the Kármán line, atmospheric density would become sufficient to generate substantial heating and ionization of the air ahead of the object. The asteroid would compress atmospheric gases so violently that the air itself would achieve plasma state, glowing with temperatures exceeding those on the sun's surface. This luminous shockwave would become visible from the ground during the final minutes before impact, an ominous harbinger racing ahead of total destruction. The shallow seawater at the impact site, only 100 meters deep at some locations, would provide essentially zero protection or deceleration. At the velocities involved, water might as well be vacuum. The asteroid would punch through the ocean layer in a fraction of a second, vaporizing it instantly and adding enormous quantities of superheated steam to the expanding fireball without meaningful loss of momentum. The underlying sedimentary rocks would fare no better. The asteroid's kinetic energy, approximately 100 million megatons of TNT equivalent, would be released in a fraction of a second, creating pressures and temperatures that would vaporize rock as easily as a blowtorch melts ice. The gravitational acceleration continued relentlessly, governed by equations that have operated unchanged since the formation of the solar system. At 90,000 kilometers, Earth's gravitational pull had strengthened to approximately 12 meters per second squared. Still, only about 1% of surface gravity, but enough to add measurable velocity with each passing second. This acceleration would increase with the square of decreasing distance, meaning that during the next 15 minutes, as the asteroid fell from 90,000 kilometers to approximately 45,000 kilometers, the gravitational force would quadruple. The asteroid's trajectory had been refined by 4 billion years of orbital mechanics into this singular convergence of rock and planet. On Earth's surface, life continued in complete ignorance of the approaching catastrophe. Across the Yucatan Peninsula and surrounding regions of what would become Mexico, Central America, and the Caribbean, ecosystems operated under the late Cretaceous spring conditions. Coastal regions teemed with marine life, mosasaurs patrolling offshore waters, fish schools moving through shallows, pterosaurs soaring above beaches. Inland forests sheltered diverse dinosaur communities adapted to tropical conditions. The limestone platform that formed the geological foundation of the region had been deposited over millions of years as countless marine organisms lived, died, and accumulated their calcium carbonate shells in thick layers. This ancient biological productivity had created the very rocks that would soon be converted to plasma and ejected into the stratosphere, the asteroid itself a 6-mile wide fragment of carbonaceous chondrite carried within its structure chemical signatures dating to the formation of the solar system 4.6 billion years ago. Presolar grains embedded in the rock predated the sun itself, formed in the atmospheres of stars that lived and died before our solar system existed. Organic compounds preserved in the asteroid's matrix represented some of the most primitive chemistry in the solar system, unchanged since the pre-solar nebula collapsed to form the planets. In a darkly ironic twist, this repository of ancient cosmic material would deliver its chemical payload to Earth in the most violent manner possible, contributing to the planet's eventual biological renewal after mass extinction. The 30-minute mark represented a threshold of sorts, the point beyond which even hypothetical advanced technology would struggle to alter the outcome. Deflection strategies depend critically on available time, as the small forces that can be practically applied require long periods to accumulate meaningful trajectory changes. At 90,000 kilometers with 30 minutes remaining, the asteroid's momentum was so enormous and the remaining time so short that no realistic intervention could prevent impact. The collision had become inevitable, not just physically, but mathematically, locked into place by the intersection of two trajectories through space-time. The angle of approach, 45 to 60 degrees from horizontal, had been determined by the orbital mechanics that brought the asteroid into Earth-crossing trajectory. This angle was not chosen or directed, but simply emerged from the gravitational interactions between the asteroid, Earth, and the other bodies of the solar system. Yet it happened to fall within the range that would maximize catastrophic consequences. Shallower angles might have caused atmospheric breakup, or grazing impacts that distributed energy over wider areas with less concentrated devastation. Steeper angles would have driven energy deeper into the crust, with less atmospheric injection of vaporized material. The actual approach angle would ensure maximum lethality, full penetration to the surface, combined with enormous quantities of impact debris blasted into the stratosphere and beyond. The energy equation remained brutally simple and utterly unforgiving. 4.2 x 1023 joules of kinetic energy was about to be converted into other forms in less than 1 second. This represented more energy than all of Earth's volcanoes had released in the previous million years, concentrated into a single point and a single instant. The crater formation process would excavate material to depths of 30 kilometers, reaching into the mantle itself and exposing rock that hadn't seen daylight in billions of years. A volume of approximately 100,000 cubic kilometers of rock would be displaced, melted, or vaporized, enough material to bury the entire state of Texas under a layer 100 meters thick. At 30 minutes before impact, these consequences remained locked in the future, their inevitability determined by physics, but their reality not yet manifest. The electromagnetic environment around the asteroid remained relatively benign at this distance, though that would change dramatically as atmospheric entry began. Space near Earth is filled with charged particles, the solar wind, trapped radiation in the Van Allen belts, and ionized atmospheric atoms at the fringes of the exosphere. The asteroid's passage through these regions would have created minor disturbances in the local electromagnetic field, but nothing that would be detectable from the surface without sophisticated instruments. The rock simply fell, following gravity's pull, electrically neutral and electromagnetically silent. The target rocks at the impact site contained within their chemistry a perfect recipe for global catastrophe. The limestone and dolomite formations consisted primarily of calcium carbonate, the accumulated shells and skeletons of marine organisms deposited over millions of years. When vaporized by impact, these carbonates would release enormous quantities of carbon dioxide into the atmosphere. Even more significantly, the thick deposits of anhydrite and gypsum, calcium sulfate minerals formed from ancient evaporated seabeds, contained massive amounts of sulfur. The impact would vaporize several hundred gigatons of sulfur-bearing rock, injecting sulfur dioxide directly into the stratosphere. This sulfur would combine with water vapor to form sulfate aerosols, tiny droplets of sulfuric acid that would remain suspended in the upper atmosphere for years, blocking sunlight and creating the prolonged impact winter that would devastate global ecosystems. If by some extraordinary chance the asteroid had struck deep ocean basalts far from any continents, or in ancient crystalline shield rocks devoid of carbonates and sulfates, the extinction might have been less severe. The kinetic energy would have been identical, the crater formation process essentially the same, but the atmospheric loading of climate-altering aerosols would have been dramatically reduced. The Yucatan target, with its thick sequences of limestone and evaporate deposits, represented an almost worst-case scenario for impact-induced environmental catastrophe. Pure chance had selected one of the most geologically unfortunate impact sites on the planet. The spring timing added another layer of vulnerability, particularly for Northern Hemisphere species. Research examining fish bones from the Tanis site in North Dakota revealed that the impact occurred during spring based on growth ring patterns. This meant many species were in breeding cycles, energy reserves were not yet fully restored after winter dormancy, and young offspring would be particularly vulnerable to environmental disruption. The seasonal timing was as random as the impact location, yet it compounded the severity of consequences for countless species whose life cycles were synchronized to annual patterns that would be catastrophically interrupted. 30 minutes before impact, the asteroid had already passed the orbits of all artificial satellites. Had Earth possessed any, it was closer to the planet than any geosynchronous satellite would orbit in the modern era. Earth's gravity was pulling the object inward with ever-increasing force, and the final acceleration phase was beginning. Within 15 more minutes, the distance would halve again. Within 20 minutes, atmospheric effects would become significant. Within 29 minutes, the asteroid would be entering the upper atmosphere, and the final violent seconds would begin. The mathematical certainty of orbital mechanics meant that scientists analyzing this event 66 million years later could reconstruct the approach trajectory with remarkable precision despite having no direct observations of the event. The laws of physics are time-symmetric. They work equally well forward and backward. By examining the crater structure, the distribution of ejecta, the chemical composition of impact debris, and the orientation of shocked rock formations, researchers could calculate backward to determine impact angle, velocity, and approach direction. The asteroid had left its signature in stone, and that signature encoded the story of its final moments. On the surface below, spring morning continued across a planet that had 30 minutes of normalcy remaining. Photosynthesis proceeded in countless plants. Predators hunted prey, herbivores consumed vegetation, marine creatures swam through warm seas. The entire biosphere hummed with activity, billions upon billions of individual organisms pursuing survival and reproduction, according to strategies refined over eons. None of them could know that within half an hour, The rules governing their world would be rewritten by forces operating on timescales beyond biological adaptation. At 15 minutes before impact, the asteroid had closed to approximately 27,000 kilometers from Earth's surface, closer than geosynchronous satellites orbit in the modern era. The object was now falling through regions where Earth's extended atmosphere began to exert measurable influence, though still far too tenuous to cause significant deceleration or heating. The gravitational acceleration had intensified dramatically as distance decreased, with Earth's pull now approaching 10% of surface gravity and strengthening exponentially with each passing second. The asteroid's velocity, relative to the surface, had increased to its terminal approach speed, somewhere between 20 and 40 kilometers per second, depending on the exact orbital geometry, with most crater modeling suggesting approximately 30 kilometers per second as the most likely impact velocity. At this speed, the object was covering nearly 1,800 kilometers every minute, the distance from New York to Dallas traversed in 60 seconds. Earth now dominated the entire forward hemisphere of the asteroid's sky, a vast globe filling the view with swirling white clouds, deep blue oceans, and the brown-green patchwork of continental landmasses. The target zone in the Gulf of Mexico and Yucatan Peninsula was clearly visible along the approach vector, though from the asteroid's perspective it appeared simply as another patch of ocean and coastline, indistinguishable from countless other regions. The shallow tropical waters covering the impact site reflected afternoon sunlight. It was late morning to early afternoon across the region that would soon be vaporized, with the sun climbing toward its zenith in clear spring skies. Beneath those waters, limestone platforms and overlying sedimentary rocks rested undisturbed. The accumulated remains of billions of marine organisms deposited over millions of years about to be converted to plasma in seconds. The physics governing these final minutes were inexorable. The asteroid's kinetic energy, approximately 4.2 x 1023 joules, remained locked in its motion, awaiting release. This energy equaled roughly 100 million megatons of TNT, or approximately 10 billion times the explosive yield of the Hiroshima atomic bomb. No natural process could dissipate or redirect this energy. The atmosphere that the asteroid was about to encounter would provide essentially zero resistance until the final seconds. Even the densest regions of the upper atmosphere at 100 kilometers altitude contained so little mass that deceleration would be negligible. The asteroid would arrive at the surface with virtually its full cosmic velocity intact, and in a fraction of a second, all that kinetic energy would be converted into heat, shock waves, and the violent displacement of crustal material. Computer simulations reconstructing these final minutes reveal the cascade of destruction about to unfold. The impact would generate pressures at the collision interface, exceeding several hundred gigapascals, millions of times atmospheric pressure, instantaneously vaporizing both the asteroid and the upper layers of target rock. Temperatures would exceed 10,000 degrees Celsius, hot enough to create plasma states where electrons separate from atomic nuclei. The shock wave would propagate through the crust at velocities exceeding the speed of sound in rock, fracturing material for hundreds of kilometers in all directions. Within the first second after contact, a crater 30 kilometers wide would have formed. An excavation would continue for several minutes as rebounding crustal material created the final structure measuring approximately 200 kilometers in diameter. The target rock composition would prove catastrophically significant. The sedimentary sequence beneath the impact site contained thick deposits of anhydrite and gypsum, calcium sulfate minerals formed from ancient evaporated seabeds. When vaporized by the impact, these sulfur-bearing rocks would inject more than 200 to 325 gigatons of sulfur dioxide directly into the stratosphere. This represented 3 times more sulfur than previous models had estimated, implying cooling effects more severe than initially calculated. The sulfur would combine rapidly with water vapor to form sulfate aerosols, tiny droplets of sulfuric acid suspended in the upper atmosphere that would block sunlight for years. Additionally, the vaporization of limestone and dolomite would release over 500 gigatons of carbon dioxide into the atmosphere, though the greenhouse warming from this CO2 would be insignificant compared to the sulfate cooling. The shallow seawater, covering the impact site, only 100 to 650 meters deep depending on exact location, would be swept aside and instantly vaporized in the first microseconds of contact. adding over 200 gigatons of water vapor to the expanding fireball. At the velocities involved, water provided no more resistance than vacuum. The asteroid would punch through the ocean layer without meaningful deceleration, its momentum essentially unchanged by the encounter. The vaporized seawater would mix with vaporized rock to create a superheated plasma plume that would expand upward and outward at tremendous velocities, carrying a toxic mixture of sulfur dioxide, carbon dioxide, water vapor, and pulverized rock into the stratosphere and beyond. The angle of approach, between 45 and 60 degrees from horizontal, arriving from the northeast, had been determined by the orbital mechanics that brought the asteroid into Earth-crossing trajectory millions of years earlier. This oblique angle would maximize the catastrophic consequences in ways that a more vertical or more shallow impact would not. Vertical impacts drive energy downward into the crust, creating deeper craters but ejecting less material into the atmosphere. Very shallow impacts can cause atmospheric breakup or grazing collisions that distribute energy over wider areas with less concentrated devastation. The actual approach angle fell within the range that would ensure maximum lethality. Full penetration to the surface combined with enormous quantities of impact debris blasted into the stratosphere and beyond. Analysis of the crater's asymmetric shape and structure has allowed scientists to reconstruct the impact geometry with precision. The asymmetry in the crater's morphology indicates the northeast to southwest trajectory, with ejecta distributed preferentially in the direction of travel. Seismic surveys across the Yucatan Peninsula have revealed the crater's complete structure, showing it possesses the same morphology as the largest impact basins on other planetary bodies like the Lees-Meitner and Clenova craters on Venus. The structure includes a peak ring approximately 80 kilometers in diameter, formed when the transient crater cavity collapsed and central uplift structures rebounded from the mantle depths reached during excavation. The ejection of material would occur in distinct phases determined by shock pressure. Rocks experiencing the highest shock pressures near ground zero would be ejected at velocities exceeding 11 kilometers per second, Earth's escape velocity, meaning this material would be permanently lost to space. Rocks experiencing slightly lower shock pressures would be launched into ballistic trajectories that would carry them hundreds to thousands of kilometers from the impact site before falling back to Earth. Material experiencing even lower shock pressures would be vaporized but remain within Earth's gravitational well, forming the ejector curtain and impact plume that would inject several thousand gigatons of material into the stratosphere. The most heavily shocked rocks near the impact point would display distinctive deformation features. Shocked quartz with multiple sets of planar deformation features, high-pressure mineral polymorphs like stishovite and coesite, and melted glass containing meteoritic signatures. At 15 minutes before impact, the asteroid crossed through the orbit altitude of the International Space Station, roughly 400 kilometers, and continued its inexorable fall. Had modern astronauts been stationed at that altitude and in the correct position, they would have witnessed the asteroid's approach as a rapidly brightening point of light, growing visibly larger with each passing second. Within minutes, it would have resolved into a distinct rocky body, its dark grey surface features becoming visible as separation decreased. The astronauts would have had perhaps 10 minutes to observe before the object dropped below their orbital altitude and plunged into the denser atmosphere, at which point the violent entry phase would begin and the view would be obscured by ionized atmospheric gases glowing with plasma temperatures. On Earth's surface, life continued in complete ignorance across the regions about to be devastated. The Yucatan Peninsula and surrounding areas of what would become Mexico, Central America, and the Caribbean hosted diverse late Cretaceous ecosystems operating at full spring productivity. Coastal regions teemed with marine life, mosasaurs patrolling offshore waters, fish schools moving through shallows, pterosaurs soaring on thermal currents above beaches. Inland forests sheltered dinosaur communities adapted to tropical conditions, with hadrosaurs feeding in wetlands, ceratopsians browsing vegetation in more open habitats, and large theropods hunting across their territories. The spring timing meant breeding seasons were underway or imminent. Nesting activities occupied many species, and energy reserves depleted by winter were still being restored through increased foraging. Further from the impact zone, across North America and beyond, countless ecosystems proceeded according to patterns refined over eons. Triceratops herds in northern regions continued their movements through river valleys. Tyrannosaurus hunted in inland forests. Along the western interior seaway, marine reptiles pursued fish in warm, shallow waters, while pterosaurs wheeled overhead. Small mammals prepared for nighttime foraging as the day progressed. Insects pollinated flowering plants, birds nested in trees. The entire biosphere hummed with activity, billions of organisms pursuing survival and reproduction according to evolutionary strategies that had proven successful for millions of years. None possessed any capacity to detect the approaching threat or any evolved response that could mitigate what was coming. The electromagnetic environment around the asteroid remained relatively quiet, though this would change dramatically within minutes as atmospheric entry effects began. The rock fell through regions of the magnetosphere where charged particles from the solar wind interacted with Earth's magnetic field. But the asteroid itself, electrically neutral and composed primarily of non-metallic carbonaceous material, generated no significant electromagnetic disturbances. It simply fell, following the gravitational gradient toward the surface, its passage marked only by the space it occupied and the subtle perturbations its mass induced in the local gravitational field. The countdown to impact had now entered its final phase. At 15 minutes remaining, the distance of approximately 27,000 kilometers would be covered in exactly that time at the current velocity, 1,800 kilometers per minute, 30 kilometers per second. Each second brought the asteroid 30 kilometers closer to collision. Each minute represented 1,800 kilometers of separation erased. The mathematics were absolute and unforgiving. 15 minutes remained until 4.2 x 1023 joules of kinetic energy would be released in a fraction of a second at a single point on Earth's surface. The impact site's geological characteristics ensured maximum climatic consequences. Had the asteroid struck in deep ocean basalts far from continental margins, or in ancient crystalline shield rocks devoid of volatile rich sediments, the immediate destruction would have been identical. But the long-term environmental effects dramatically reduced. The Yucatan target, with its kilometers-thick sequence of limestone, dolomite, anhydrite, and gypsum, represented nearly the worst-case scenario for impact-induced climate catastrophe. Pure chance had selected this particular location out of all possible impact sites on Earth, and that chance selection would prove decisive in determining the severity and duration of the extinction event. Research examining the climatic effects has revealed that the sulfate aerosols produced by vaporizing the sulfur-rich target rocks would reduce solar transmission to only 10 to 20% of normal levels for a period of 8 to 13 years. More recent studies suggest that silicate dust from pulverized rocks would persist even longer, approximately 15 years, and prove particularly effective at blocking the wavelengths of light required for photosynthesis. The combination of sulfate aerosols and silicate dust would drive global surface temperatures down by 5 to 31 degrees Celsius, with modeling suggesting near-freezing conditions possible even in tropical regions. This extended impact winter would shut down photosynthesis on land and in oceans, collapsing food webs from the bottom up and ensuring that the extinction would not be limited to creatures killed directly by the impact. Blast wave and thermal pulse would radiate outward from the impact site at devastating velocities. Winds exceeding 1,000 kilometers per hour would scour the land within a radius of 900 to 1,800 kilometers, shredding vegetation and killing any animals in nearby ecosystems. The travel time for these blast effects was measured in minutes, meaning destruction would spread across vast areas before the first returning ejector even began falling back through the atmosphere. The pressure pulse alone would be lethal across distances comparable to the width of a continent, and this represented merely the initial destructive phase before the longer-term climate effects took hold. At 15 minutes before impact, all these consequences remained locked in potentiality, their inevitability determined by physics, but their reality not yet manifest. The asteroid continued its silent fall through increasingly dense atmospheric layers, and on Earth below, the final quarter hour of the Mesozoic era proceeded in complete normalcy. Predators hunted prey, herbivores consumed vegetation, marine creatures swam through warm seas, plants photosynthesized in sunlight, decomposers processed dead organic matter. The entire planetary biosphere operated according to rules established over 4 billion years of evolution. Within 15 minutes, those rules would be suspended, and a new era would begin, one that would eventually lead to the rise of mammals and, ultimately, to a species capable of reconstructing what happened on that catastrophic day 66 million years ago. At 5 minutes before impact, the asteroid had closed to approximately 9,000 kilometers from Earth's surface, roughly the diameter of the planet itself. The object was now plunging through regions of the thermosphere where atmospheric density, though still incredibly tenuous, had begun to increase measurably. Individual air molecules struck the asteroid's leading surface with growing frequency, each collision converting a tiny fraction of kinetic energy into heat. The cumulative effect remained negligible at this altitude, but the process had begun. The asteroid's silent journey through vacuum was transitioning into a violent interaction with Earth's atmosphere that would dominate the final minutes. Earth's gravitational pull had intensified to approximately 60% of surface gravity, accelerating the object continuously as it fell through the final thousands of kilometers of separation. The asteroid's velocity had stabilized. At its terminal approach speed, computer models and crater morphology studies consistently point to approximately 20 to 30 kilometers per second as the most likely impact velocity, with many analyses favoring the upper end of this range. At 30 kilometers per second, the asteroid was now only 5 minutes, 300 seconds from collision. Each second eliminated 30 kilometers of separation. Each minute brought it 1 through 800 kilometers closer to the surface. The mathematics were absolute. Distance remaining divided by velocity yielded time remaining. And that calculation produced an answer, measured in single-digit minutes. From the asteroid's perspective, if such an object could be said to have a perspective, Earth had transformed from a distant, blue disk into an overwhelming presence filling the entire forward hemisphere. The target zone in the Gulf of Mexico was now clearly visible as a specific patch of shallow tropical water, though from 9,000 kilometers altitude, the ocean's depth appeared uniform and gave no indication of the geological time bomb hidden beneath the seafloor. The Yucatan Peninsula's limestone platform, the thick sedimentary sequences containing anhydrite and gypsum, the overlying ocean water, all of it appeared simply as another unremarkable patch of planetary surface about to receive the full force of 4.2x 1023 joules of kinetic energy. The approach trajectory, angled between 45 and 60 degrees from horizontal, arriving from the northeast, was now fixed with absolute finality. The asteroid would strike the shallow sea with its full cosmic velocity essentially intact, punch through the water column in milliseconds without meaningful deceleration, and drive into the underlying crust with pressures exceeding several hundred gigapascals. The impact angle would maximize the volume of vaporized material ejected into the stratosphere, while ensuring complete penetration to depths reaching the mantle itself. Within seconds of contact, temperatures at the impact interface would exceed 10,000 degrees Celsius, hot enough to vaporize rock instantaneously and create plasma states, where matter exists as separated nuclei and free electrons. The physical processes about to unfold had been reconstructed through decades of research combining crater analysis, impact modeling, laboratory experiments, and geological evidence preserved in the KPG boundary layer. Within the first microseconds after contact, a shock wave would propagate through both the asteroid and the target rocks at velocities exceeding 10 kilometers per second, faster than the speed of sound in rock. This shock wave would compress material to densities far beyond normal states, generating the immense pressures that would vaporize and melt thousands of cubic kilometers of rock. The asteroid itself would be completely destroyed, converted from a solid, 6-mile-wide object into an expanding cloud of superheated vapor mixed with vaporized target rock. The ejection of material would begin within the first second and continue for several minutes. The most heavily shocked rocks near ground zero would be accelerated to velocities exceeding 11 kilometers per second, Earth's escape velocity, and would be permanently lost to space, eventually dispersing throughout the solar system. Material experiencing slightly lower shock pressures would be launched on ballistic trajectories, carrying it hundreds to thousands of kilometers from the impact site before falling back to Earth hours later. The returning ejector would re-enter the atmosphere at such high velocities that friction heating would raise global atmospheric temperatures sufficiently to ignite vegetation across vast distances. An estimated 70% of Earth's forests would burn in the hours following impact, adding massive quantities of soot to an atmosphere already laden with dust and sulfate aerosols. 5 minutes before impact, the asteroid crossed through the altitude where low Earth orbit satellites would operate in the modern era, approximately 400 to 2,000 kilometers above the surface. Had the planet been ringed with spacecraft and telescopes as it would be 66 million years in the future, astronomers would have had perhaps 3 to 4 minutes of direct visual observation before the object dropped into the denser atmosphere and atmospheric effects obscured the view. The asteroid would have appeared as a dark, irregular body tumbling slowly through space, its rough carbonaceous surface reflecting little sunlight, growing visibly larger with each passing second as separation decreased. Within 2 minutes, it would resolve from a point of light into a distinct rocky mass. Within 4 minutes, surface features, impact craters, ridges, fractures, would become visible. At the 5-minute mark, the asteroid was close enough that its apparent size would be growing perceptibly, doubling in angular diameter approximately every minute. The thermosphere, through which the asteroid was now falling, contained atmospheric densities approximately 1/1,000,000th those at sea level, still nearly perfect. Vacuum by everyday standards, but sufficient to begin generating measurable heating effects at the tremendous velocities involved. Air molecules striking the asteroid's leading surface were being compressed and ionized by the shockwave building ahead of the object, creating a thin envelope of glowing plasma that marked the beginning of visible atmospheric entry effects. From the ground, had anyone been looking in precisely the right direction at precisely the right moment, the asteroid might have become barely visible as an extraordinarily bright meteor, though at 5 minutes from impact, it remained too high and too distant to be obvious to casual observers. On Earth's surface across the impact zone, afternoon was progressing normally. The spring sun climbed toward its daily maximum, warming land and water under clear skies typical of the late Cretaceous greenhouse climate. The shallow tropical seas covering the future impact site reflected sunlight in patterns modulated by wind and current. Beneath those waters, marine life continued its daily activities. Fish schools moved through the water column, marine reptiles hunted, invertebrates fed on the seafloor. None possessed any capacity to detect the approaching object, or any evolved response that might provide warning or protection. The ocean would offer no sanctuary. The asteroid would vaporize the entire water column instantly, and the ensuing tsunami would reach heights exceeding 100 meters, scouring coastlines for thousands of kilometers in all directions within hours of impact. The target rocks beneath, the impact site contained within there, chemistry the ingredients for prolonged global catastrophe. The thick deposits of anhydrite and gypsum, calcium sulfate minerals formed from ancient evaporated seabeds, would release more than 325 gigatons of sulfur dioxide when vaporized by the impact. This sulfur would combine with atmospheric water vapor to form sulfate aerosols that would persist in the stratosphere for years, blocking sunlight and driving global temperatures down by as much as 5 to 31 degrees Celsius, depending on latitude and local conditions. The limestone and dolomite formations would release over 500 gigatons of carbon dioxide, though the greenhouse warming from this CO2 would be overwhelmed by the cooling effects of the sulfate aerosols and silicate dust. Recent research has revealed that fine silicate dust from pulverized rocks would prove particularly devastating to photosynthetic organisms. This dust would remain suspended in the atmosphere for approximately 15 years, far longer than previously estimated, and was especially effective at blocking the specific wavelengths of light required for photosynthesis. The combination of sulfate aerosols, silicate dust, and soot from wildfires would reduce solar transmission to only 10 to 20% of normal levels, shutting down photosynthesis on land and in oceans, and collapsing food webs from the bottom up. This extended impact winter would ensure that the extinction would not be limited to creatures killed directly by the impact, but would propagate through ecosystems worldwide as primary productivity ceased and herbivores starved, followed by the carnivores that depended on them. At 5 minutes before impact, all these consequences remained locked in futurity, their inevitability determined by the laws of physics, but their reality not yet manifest. The asteroid continued its accelerating plunge through the thermosphere, and on the surface below, the final 5 minutes of the Mesozoic era proceeded in complete normalcy. The energy contained in the asteroid's motion, approximately 100 million megatons of TNT equivalent, represented more than all of Earth's active volcanoes had released in the previous million years, concentrated into a single object and about to be delivered to a single point in a fraction of a second. The nearest comparison in human experience would be nuclear weapons. But even the largest thermonuclear device ever detonated, the Soviet Tsar bomber at 50 megatons, represented only 0.0005% of the asteroid's kinetic energy. It would require 2 million such weapons detonated simultaneously to equal the energy about to be released. The scale transcended human experience entirely, operating in realms where intuition fails and only mathematical calculation can convey the magnitude of what was approaching. The crater that would be excavated by this impact would measure approximately 200 kilometers in diameter and reach depths of 30 kilometers, deep enough to penetrate through the entire sedimentary sequence, through the limestone platform, through the full thickness of continental crust, and into the upper mantle. The excavation would displace approximately 100,000 cubic kilometers of rock, ejecting much of it as vapor and molten material, while heaving the remainder outward in concentric rings that would form the crater's complex structure. The transient crater cavity, the initial hole punched by the impact, would form within seconds, but the final crater structure would take several minutes to develop, as shocked rock rebounded from mantle depths to create the peak ring visible in seismic surveys of the buried structure. The blast wave radiating outward from the impact would travel through the atmosphere at supersonic velocities, creating winds exceeding 1,000 kilometers per hour across distances of 900 to 1,800 kilometers. Everything within this radius would be scoured by hurricane-force winds far more powerful than any storm Earth's climate could naturally generate. Trees would be uprooted and shredded, animals would be killed by the pressure wave or by flying debris. The landscape would be stripped to bedrock in the nearest zones, with destruction diminishing gradually with distance, but remaining catastrophic across areas comparable to the size of continents. And this represented merely the initial mechanical destruction. The thermal pulse, the returning ejecta, the wildfires, the tsunamis, and the long-term climate effects would add layers of devastation that would extend the catastrophe both spatially and temporally, far beyond the immediate impact zone. At 5 minutes before impact, the asteroid had entered its terminal approach phase. The distance of approximately 9,000 kilometers would be covered in exactly 300 seconds at the current velocity of 30 kilometers per second. The countdown had entered single digits, 5 minutes, then 4, then 3, each minute bringing the object 1,800 kilometers closer to collision, each second eliminating 30 kilometers of separation. The gravitational acceleration continued, governed by Newton's equations, pulling the asteroid inward with exponentially increasing force as distance decreased. There was no longer any possibility of deflection, no hypothetical intervention that could alter the outcome. The collision was now measured in minutes, and those minutes were passing with inexorable regularity. On the surface below, across the regions about to be devastated, life continued in patterns refined over hundreds of millions of years. Pterosaurs soared on thermal currents above the Gulf of Mexico, their keen eyes scanning for fish moving near the surface. Marine reptiles, mosasaurs and plesiosaurs, hunted in the warm, shallow seas, pursuing prey through water that would soon be vaporized. Along coastlines, hadrosaurs fed in wetlands while ceratopsians browsed vegetation in more open habitats. Theropods moved through forests, hunting or scavenging according to their specialized adaptations. Small mammals prepared for nighttime activity as afternoon progressed. Insects pollinate flowers. Birds nested in trees. The entire biosphere operated according to evolutionary programming that had proven successful for eons. 5 minutes remained until that programming became obsolete, until the rules governing life on Earth would be suspended and rewritten by forces operating on timescales measured in seconds rather than generations. The asteroid fell silently through increasingly dense atmospheric layers, its dark surface beginning to glow faintly as friction, heating intensified, and on the planet below, the final moments of the Mesozoic era counted down towards zero. At approximately 66.0 million years before the present moment, the Chicxulub asteroid made contact with Earth's surface. The collision occurred in shallow tropical waters of the Gulf of Mexico at coordinates that would someday be mapped as the northern Yucatan Peninsula. The asteroid, approximately 10 to 15 kilometers in diameter and traveling at roughly 20 to 30 kilometers per second, struck at an oblique angle between 45 and 60 degrees from horizontal, approaching from the northeast. In the first microsecond of contact, pressures at the impact interface exceeded several hundred gigapascals, millions of times atmospheric pressure, instantly vaporizing both the asteroid and the uppermost layers of target rock. Temperatures spiked beyond 10,000 degrees Celsius, creating a plasma fireball where matter existed in states normally found only in stellar interiors. The Mesozoic era, which had begun 186 million years earlier, ended in that fraction of a second. The physics of hypervelocity impact governed what happened next. When objects collide at speeds exceeding several kilometers per second, the materials involved behave more like fluids than solids. Rock flows, deforms, and vaporizes under pressures and temperatures that overwhelm the molecular bonds holding matter together. The asteroid punched through the 100 to 650 meters of seawater without meaningful deceleration, vaporizing it instantly and adding over 200 gigatons of superheated steam to the expanding fireball. The underlying sedimentary rocks, limestone, dolomite, anhydrite, and gypsum accumulated over millions of years, offered no more resistance than the water. The asteroid's momentum carried it downward through kilometers of sediment in the first few seconds, vaporizing and melting everything in its path while transferring its enormous kinetic energy to the surrounding crust. Within the first second after contact, a shock wave propagated outward through the crust at velocities exceeding 10 kilometers per second. This wasn't sound or earthquake waves, but a compression wave traveling through solid rock faster than seismic energy, fracturing and shattering material for hundreds of kilometers in all directions. The shock pressures deformed quartz crystals in ways that only occur under extreme conditions, creating microscopic planar deformation features that would serve as diagnostic evidence of impact when geologists discovered them 66 million years later. High-pressure mineral polymorphs like stishovite and coesite formed in the shock zone, their presence proving that the target rocks had experienced pressures exceeding 100,000 atmospheres. The transient crater cavity, the initial hole, punched by the impact, formed within approximately 10 seconds. The excavation proceeded through two distinct phases. The initial compression stage, where the asteroid's momentum drove material downward and outward, followed by the excavation stage, where the compressed material rebounded and was ejected from the growing cavity. The transient crater reached depths of approximately 30 kilometers, penetrating through the entire sedimentary sequence, through the 35-kilometer thick continental crust and into the upper mantle. For several seconds, rock from depths that hadn't seen sunlight in billions of years was exposed at the surface, superheated to temperatures where it existed as molten or vaporized material. The amount of energy released in this process defied comprehension. Approximately 4.2x 1023 joules, 100 million megatons of TNT equivalent, or 10 billion times the energy of the Hiroshima atomic bomb, was converted from kinetic energy into other forms in less than 1 second. Most of this energy went into heating and vaporizing rock, generating shock waves, creating seismic disturbances, and launching material on ballistic trajectories. The immediate effect was the creation of a fireball of superheated plasma expanding upward and outward at tremendous velocity, reaching altitudes of 70 kilometers or more within the first minute, and eventually injecting approximately 25 trillion metric tons of material into the atmosphere and beyond. The ejector from the impact was stratified by velocity and shock pressure. Material experiencing the highest shock pressures near ground zero was accelerated to velocities exceeding Earth's escape velocity of 11 kilometers per second. This rock was lost to space permanently, eventually dispersing throughout the solar system as asteroid impact-derived meteorites. Some of this material has likely been found on the Moon, Mars, and even as meteorites that have fallen back to Earth millions of years after their violent ejection. Material experiencing slightly lower shock pressures was launched on ballistic trajectories that would carry it hundreds to thousands of kilometers from the impact site, with flight times ranging from minutes to hours depending on ejection, velocity, the fine-grained ejector, material, shocked to lower pressures but still melted or pulverized into tiny particles, was lofted into the stratosphere where it would remain suspended. For months to years, this dust cloud consisted primarily of silicate minerals ground to microscopic dimensions, along with sulfate aerosols formed when the vaporized sulfur-bearing target rocks combined with atmospheric water vapor. Research examining the composition of the KPG boundary layer worldwide has revealed that this airborne material contained elevated concentrations of iridium, an element rare in Earth's crust but abundant in asteroids, providing the chemical fingerprint that would eventually allow scientists to identify the impact as the cause of the mass extinction. The crater modification phase began within seconds after the initial excavation and continued for several minutes. The transient crater cavity, unstable due to its immense depth relative to diameter, immediately began collapsing inward under gravitational forces. Rock from the crater walls slumped inward, while simultaneously, material from the crater floor rebounded upward from the compression it had experienced during excavation. This rebound was dramatic. Mantle rock from depths of 30 kilometers surged upward to form a central peak that temporarily rose several kilometers above the original surface before collapsing outward to create the peak ring visible in seismic surveys of the buried crater. The peak ring formation occurred within minutes of impact, as material rebounding from mantle depths spread outward in a circular mountain range approximately 80 kilometers in diameter. Core samples drilled from this peak ring in 2016 revealed granite that had been buried deep within the continental crust, rock that hadn't seen daylight in billions of years, now exposed at the surface, shocked by immense pressures and partially melted in just minutes. The drill core provided a geological document stretching hundreds of feet, with over 400 feet of melt rock laid down during the day following impact, preserving a minute-by-minute record of the catastrophe. The seismic energy released by the impact propagated through Earth's crust as powerful earthquake waves. The magnitude has been estimated at somewhere between magnitude 10 and 11 on the Richter scale, far beyond any earthquake in recorded human history. These seismic waves traveled at velocities of several kilometers per second through the crust, reaching distant locations within minutes to hours, depending on distance. At the Tsunamis site in North Dakota, approximately 3,000 kilometers from the impact, seismic waves arrived within approximately 13 to 30 minutes after impact, causing massive seismic activity in rivers and inland waterways that created the preserved inundation deposits containing impact ejecta and shocked fish. The thermal pulse from the impact radiated outward in all directions. The expanding fireball, a sphere of superheated plasma with temperatures exceeding 10,000 degrees Celsius, emitted thermal radiation across the electromagnetic spectrum. This intense heat was felt at distances exceeding 1,500 kilometers from ground zero, with temperatures sufficient to ignite vegetation and kill exposed animals. But this initial thermal pulse was brief, lasting only seconds to minutes before the fireball cooled and the direct line of sight heating ceased. The more sustained and widespread thermal effects would come hours later when the returning ejecta re-entered the atmosphere. Within the first 10 minutes after impact, the crater had achieved approximately its final diameter of 200 kilometers, though modification continued as material continued to settle and the newly formed peak ring stabilized. The shallow sea that had covered the impact site had been vaporized and displaced, leaving a temporary hole in the ocean approximately 200 kilometers wide. Water from the surrounding Gulf of Mexico began rushing back toward the crater almost immediately, creating chaotic water movements that would persist for hours. The drill core from the peak ring shows more than 260 feet of rock deposited by surges of water rushing back into the crater in the minutes and hours following impact, carrying melted stone and shocked debris. By 10 minutes after impact, the worst of the immediate mechanical destruction within the crater was complete. But the global catastrophe was only beginning to unfold. The expanding ejecta cloud rose vertically above the impact site, reaching altitudes of 70 kilometers or more within the first several minutes. This towering column of vaporized rock, water vapor, and shock-heated gases began spreading laterally at high altitudes, forming a mushroom cloud structure vastly larger than any nuclear explosion. The upper portions of this cloud achieved velocities sufficient to begin circumnavigating the planet, initiating the global distribution of impact debris that would eventually deposit the KPG boundary layer on every continent. The vaporization of sulfur-rich target rocks injected more than 325 gigatons of sulfur dioxide directly into the stratosphere. This represented approximately 3 times more sulfur than earlier models had estimated, based on analysis showing that the gypsum and anhydrite layers beneath the impact site had been almost entirely removed and vaporized into the atmosphere. The sulfur dioxide began combining with water vapor immediately, forming sulfate aerosols, tiny droplets of sulfuric acid that would remain suspended in the upper atmosphere for years. These aerosols would prove devastating to Earth's climate, blocking sunlight and driving temperatures downward in a prolonged impact winter. The mega tsunami generated by the impact began radiating outward from the crater within minutes. When the asteroid struck in shallow seas, only 100 to 650 meters deep, the displacement of water was enormous. The initial wave height has been estimated at more than 100 meters, comparable to a 30-story building, as it left the impact zone. This massive wave spread outward in all directions, traveling at hundreds of kilometers per hour across the Gulf of Mexico and Caribbean Sea. Had the impact occurred in the deep ocean, the tsunami would have been less catastrophic locally, though modeling suggests wave heights in deep water could have reached 4.6 kilometers. The shallow water impact created maximum coastal devastation across the nearest shorelines. Within the first hour, the tsunami struck coastlines throughout the Gulf of Mexico region, washing hundreds of kilometers inland in low-lying areas and scouring everything in its path. Fossiliferous sedimentary rocks deposited during the impact have been found throughout the Gulf region, including tsunami wash deposits containing remains of mangrove-type ecosystems, indicating that water sloshed back and forth repeatedly after the initial impact. Dead fish and other marine organisms were left in shallow waters, where they remained undisturbed by scavengers, suggesting the scavengers themselves had been killed. The wave deposits extended into what is now northeastern Mexico, northeastern Brazil, and were preserved in Atlantic deep-sea sediments, thousands of kilometers from the impact site. The crater itself recorded the chaos of these first hours. A distinct layer of sediments containing gravel, sand, and charcoal was deposited by the returning tsunami, which was reflected back toward the crater after striking distant shorelines. This layer sits atop the earlier surge deposits and melt rock, creating a stratigraphic sequence that preserves a chronological record of the first 24 hours following impact. The presence of charcoal in tsunami deposits provides direct evidence that wildfires had already begun inland, with debris from burned forests washing out to sea and accumulating in the crater. The impact had triggered wildfires through multiple mechanisms. The initial thermal pulse ignited vegetation within direct line of sight to the fireball across distances of more than 1,500 kilometers. But the more widespread ignition would come in the hours following impact, when ejecta that had been launched on ballistic trajectories began re-entering the atmosphere. This returning material, traveling at velocities of several kilometers per second, generated friction heating as it plowed through the atmosphere, creating thermal radiation intense enough to ignite vegetation across vast distances. Conservative estimates suggest that approximately 70% of Earth's forests burned in the days following impact, though some models indicate the percentage could have been higher. By the end of the first hour, the immediate mechanical effects of the impact within several thousand kilometers were complete, but the global consequences were accelerating. The blast wave had already killed everything within roughly 1,800 kilometers of ground zero. The tsunami had devastated coastlines throughout the Gulf region. Seismic waves had reached most of North America and were propagating through Earth's crust toward distant continents. The ejecta cloud was beginning its global distribution, and returning material had started igniting fires on multiple continents. The Mesozoic era had ended in seconds, but the Cenozoic era was being born in violence that would persist for hours, days, and years. The first 60 minutes following impact witnessed the transformation of a localized catastrophe into a planetary crisis. Within the immediate vicinity of the crater, a zone extending roughly 900 to 1,800 kilometers from ground zero, virtually nothing survived. The blast wave had scoured the landscape. Winds exceeding 1,000 kilometers per hour had shredded vegetation and killed all animals, and the thermal pulse had incinerated anything combustible. This zone of total devastation encompassed an area larger than Texas, a region where the Cretaceous ecosystem was not merely damaged but completely erased. The limestone platforms, the coastal forests, the shallow seas teeming with life, all had been replaced by a hellscape of pulverized rock, molten debris and raging fires. Beyond this zone of immediate annihilation, the effects were less absolute but still catastrophic. At the Tsunamis site in southwestern North Dakota, approximately 3,000 kilometers from the impact, the seismic waves arrived within 13 to 30 minutes, generating powerful seismic activity in river systems. These standing waves, created when seismic energy caused water to slosh back and forth in confined channels, inundated riverbanks and floodplains, with surges reaching heights of several meters. Fish swimming in these rivers were subjected to violent water movements, rapid pressure changes, and bombardment by impact ejecta falling from the sky. Examination of fossil fish from Tsunamis shows paddlefish and sturgeon that died instantly. their gills clogged with impact spherules, their bodies preserved in contorted positions, suggesting sudden death. The impact spherules found at Tanis and other sites worldwide provide a timeline for the global distribution of ejecta. These glass beads formed when molten rock droplets were ejected into the atmosphere and solidified while airborne, began falling back to Earth. Within minutes to hours of impact, depending on their size and ejection velocity, physics calculations indicate that ejecta arrival at Tanis occurred within approximately 13 minutes to 2 hours after impact, giving scientists an unprecedented temporal resolution in the fossil record. The spherules range in size from microscopic particles to beads several millimeters across, their chemical composition matching the target rocks at Chicxulub and confirming their origin. The ejecta followed ballistic trajectories determined by their ejection velocity and angle. Material launched at lower velocities fell back relatively close to the impact site, while material ejected at higher velocities traveled thousands of kilometers before re-entering the atmosphere. The returning ejecta generated intense friction heating as it plowed through the atmosphere at velocities of several kilometers per second, creating thermal radiation comparable to sitting beneath multiple suns. This thermal pulse would prove more sustained and geographically widespread than the initial fireball radiation, as ejecta continued raining down for hours across multiple continents. The ignition of global wildfires began within the first hour and accelerated through the remainder of the first day. The mechanism was straightforward. Returning ejecta heated the atmosphere through friction, and this atmospheric heating was transmitted to the ground through thermal radiation. Vegetation exposed to this radiation spontaneously ignited across vast areas. The fires spread rapidly through late Cretaceous forests that had experienced drought conditions in some regions and were laden with combustible organic matter accumulated over millennia. Charcoal layers found in KPG boundary deposits worldwide preserve evidence of these fires, with soot particles showing chemical signatures consistent with the combustion of terrestrial vegetation. The atmospheric composition began changing within the first hour as vaporized target rocks mixed with ambient air. The 325 gigatons of sulfur dioxide released by vaporizing gypsum and anhydrite started combining with water vapor to form sulfate aerosols. The more than 500 gigatons of carbon dioxide released from vaporized limestone and dolomite entered the atmosphere along with over 200 gigatons of water vapor from the vaporized ocean. This toxic cocktail of gases, mixed with silicate dust from pulverized rocks, began spreading through the stratosphere, initiating the atmospheric loading that would eventually block sunlight and trigger the prolonged impact of winter. The megatsunami continued its devastating progress across the Gulf of Mexico and surrounding seas throughout the first hour. Wave heights exceeded 100 meters as the tsunami left the immediate impact zone, traveling at hundreds of kilometers per hour across shallow waters. The wave struck coastlines of what would become Texas, Louisiana, Florida, and the entire Caribbean region within 30 to 60 minutes of impact, depending on distance and bathymetry. Coastal ecosystems were scoured to bedrock across vast stretches, with water penetrating hundreds of kilometers inland in low-lying areas. The tsunami deposits preserved in the geological record show characteristic graded bedding, coarser material at the bottom deposited by the initial surge, finer material at the top deposited as water velocity decreased, along with jumbled masses of organic debris, uprooted trees, and the remains of marine and terrestrial organisms mixed together in chaotic deposits. Within the crater itself, the chaos of crater modification continued throughout the first hour. The drill core obtained from the peak ring in 2016 shows more than 260 feet of material deposited by water surges rushing back into the crater during this period. These surge deposits contain melted rock, shocked granite ejected from deep within the crust, and debris carried from distances of tens to hundreds of kilometers. The crater represented a temporary hole in the ocean floor 200 kilometers wide, and the surrounding water responded to this disruption with violent sloshing that persisted for hours as the Gulf of Mexico sought equilibrium. Each surge deposited another layer of material, creating a stratigraphic sequence that preserves a minute-by-minute chronicle of events. During the first day after impact, the seismic energy from the impact continued propagating through Earth's crust throughout the first hour, triggering earthquakes along existing fault lines and potentially triggering volcanic activity in some regions, though the extent of impact-induced volcanism remains debated among geologists. The magnitude of the impact-generated seismic waves, estimated at magnitude 10 to 11, exceeded any earthquake in the geological record accessible to human observation. These waves traveled through the crust at velocities of several kilometers per second, meaning that by the end of the first hour, the seismic disturbance had reached most of the Western Hemisphere and was beginning to affect the Eastern Hemisphere. Animal behavior during this first hour, in regions far enough from the impact to avoid immediate annihilation, can only be inferred from the fossil record and our understanding of animal responses to natural disasters. The seismic shaking would have been felt across thousands of kilometers, likely causing panic and flight responses in animals capable of rapid movement. Birds and pterosaurs might have taken flight en masse, though this would offer no protection from what was coming. Terrestrial dinosaurs may have attempted to flee, though there was nowhere to flee to and no evolutionary programming to guide such flight. Marine reptiles in distant oceans would have felt seismic waves through the water but would have had no context for interpreting these signals as harbingers of doom. The returning ejecta created a spectacle that would have been visible across vast distances during the first hour. Material launched on high ballistic trajectories began re-entering the atmosphere over regions thousands of kilometers from the impact site, creating brilliant meteor displays as the rock fragments burned through friction heating. But these were not the benign shooting stars that occasionally grace modern skies. These were millions of fragments entering simultaneously, creating thermal radiation that progressively heated the atmosphere and ground surface below to temperatures capable of igniting vegetation. Any animals that had survived the initial blast wave and thermal pulse now faced a second deadly challenge. The sky itself had become lethal, raining fire from above. By the end of the first hour, smoke plumes from wildfires were rising into the atmosphere across multiple continents, adding soot to the growing atmospheric burden of dust and sulfate aerosols. The sky had begun to darken as the expanding dust cloud spread outward from the stratospheric injection point above the crater. Temperatures at ground level, in regions not yet burning, had begun to rise as returning ejecta heated the atmosphere. Marine ecosystems beyond the immediate tsunami zone continued operating normally, unaware that the atmospheric changes underway would soon disrupt ocean. Chemistry and collapse marine food webs from the bottom up. The atmospheric dust loading during the first hour represented only the beginning of what would eventually become a global shroud. The fine silicate dust ejected into the stratosphere, pulverized rock ground to particle sizes measured in micrometers, began spreading laterally in stratospheric winds. This dust was particularly effective at blocking the wavelengths of light required for photosynthesis, more so than the sulfate aerosols that would form over subsequent hours and days. Research examining the particle size distribution and optical properties of impact-generated dust has revealed that silicate dust would persist in the atmosphere for approximately 15 years, far longer than previously estimated. During the first hour, this dust was still concentrated primarily above and downwind of the impact site, but stratospheric circulation patterns would ensure global distribution within days to weeks. The crater continued to settle and stabilize throughout the first hour. Though the violence had decreased from the initial seconds, the peak ring, that circular mountain range of shocked granite thrust upward from crustal depths, had achieved approximately its final form. Though minor adjustments continued as the newly formed structure equilibrated under gravitational forces. The melt rock deposited during the first minutes after impact had begun to cool, though temperatures remained far above ambient for hours. The returning water surges deposited successive layers of debris, each surge slightly less energetic than the previous one as the system gradually dissipated energy and approached equilibrium. The returning ejecta began its deadly rain across this regional zone within minutes to tens of minutes after impact, depending on distance and the ballistic trajectories of individual fragments. The larger fragments, rocks ranging from pebbles to boulders, struck the ground at velocities sufficient to excavate small impact craters and kill anything they hit directly. But the more widespread danger came from the countless smaller fragments and the atmospheric heating they generated through friction. The cumulative effect of millions of fragments simultaneously re-entering the atmosphere was to heat the air to temperatures comparable to the inside of an oven, creating thermal radiation that ignited vegetation and killed exposed animals across vast areas. The wildfires ignited during the first hour spread rapidly through late Cretaceous forests within the regional destruction zone. The fires were fed by abundant dead wood drought-stressed vegetation in some areas, and the additional fuel provided by animals and plants killed by the blast wave and thermal pulse. Smoke plumes rose to altitudes of several kilometers, merging into massive pyrocumulonimbus clouds that generated their own weather systems. Lightning strikes that ignited additional fires, powerful winds that spread flames rapidly, and convection currents that lofted soot particles into the stratosphere. The charcoal layers preserved in KPG boundary sediments from this region are often centimeters thick, indicating widespread and intense combustion. Marine environments within the regional zone experienced profound disruption beyond the immediate tsunami effects. The impact vaporized enormous quantities of seawater, creating a temporary void in the ocean and altering salinity patterns as water rushed back into the crater from surrounding regions. The heat released by the impact raised water temperatures substantially in the Gulf of Mexico, potentially approaching boiling points in the nearest zones. Marine organisms experienced rapid temperature changes, violent water movements, pressure fluctuations, and suspension of sediments that reduced light penetration and disrupted photosynthesis by marine phytoplankton. The combination of physical trauma from the tsunami, thermal stress, and rapid environmental changes caused mass mortality in marine ecosystems, comparable to the terrestrial devastation. The atmospheric chemistry within the regional destruction zone began changing dramatically during the first hour. The vaporization of sulfur-rich target rocks created a dense cloud of sulfur dioxide directly above the impact site, with concentrations reaching toxic levels in the lower atmosphere across the region. This sulfur dioxide combined rapidly with water vapor to form sulfuric acid, creating acid rain that began falling across the region within hours. The pH of rainwater dropped to levels comparable to battery acid, sterilizing soils and poisoning any water bodies where it accumulated. The combination of thermal damage, mechanical destruction, and chemical poisoning ensured that recovery would be impossible until atmospheric circulation dispersed the toxins and weathering neutralized the acidified soils. Seismic effects within this regional zone were profound and sustained. The magnitude 10 to 11 earthquake generated by the impact caused ground accelerations far beyond anything in modern experience. Liquefaction occurred in sediment-rich soils, causing the ground to behave like fluid and swallowing anything resting on the surface. Landslides and rockfalls occurred wherever topographic relief existed, burying valleys and filling river channels with debris. The seismic shaking persisted for several minutes as waves bounced through the crust, subjecting the landscape to repeated cycles of violent ground motion. For animals attempting to flee, the ground itself betrayed them. Solid earth transformed into a treacherous, unstable surface where footing was impossible. The immediate post-impact environment within the first 1,000 miles represented conditions utterly alien to Cretaceous ecosystems. Where thriving tropical forests had existed minutes earlier, there was now scorched earth, pulverized rock, and raging fires. Where shallow tropical seas had teemed with marine life, there was turbid water laden with debris, abnormally heated and contaminated with impact ejecta. The air was thick with dust, smoke, and toxic gases. Sulfur dioxide, carbon dioxide, water vapor superheated to steam. Visibility would have been measured in meters at best, with the sun obscured by the dense atmospheric loading. Oxygen concentrations may have dropped as fires consumed available oxygen faster than photosynthesis could replenish it, creating hypoxic conditions that stressed any survivors. The few organisms that managed to survive within this zone shared common characteristics. They were small, capable of sheltering in protected microenvironments, and physiologically robust to extreme conditions. Burrow-dwelling mammals had advantages. Their underground retreats provided protection from thermal radiation, blast effects, and the immediate rain of ejecta. Aquatic organisms at depth in rivers and lakes avoided the worst thermal effects, though they would face subsequent challenges from sediment loading, temperature changes, and eventual starvation. Seeds and spores preserved in soil had no awareness or agency, but possessed the passive advantage of being small, protected, and capable of remaining dormant until conditions improved. The large-bodied dinosaurs, pterosaurs, and marine reptiles that had dominated these ecosystems had no such advantages. Their size, which had been adaptive under normal conditions, became a liability when shelter and resources became critically limited. By the end of the first hour, the regional destruction zone had been transformed from a thriving Cretaceous ecosystem into a post-apocalyptic landscape. The crater itself remained a churning maelstrom of water, debris, and settling rock, with surges still rushing in and out as the Gulf of Mexico sought equilibrium. The surrounding lands burned under skies darkened by smoke and dust. The air itself hot enough to burn lungs and sear tissues. The seas roiled with abnormal currents and temperatures, their water columns mixed to unprecedented depths by the tsunami's violence. Every ecological relationship, every food web, every evolved interdependency had been severed simultaneously. The regional ecosystem had not merely been damaged, it had been reset to zero, the biological clock set back to conditions not seen since the earliest days of multicellular life. Recovery would require not years, but millions of years as new species evolved to fill the emptied niches. Beyond the zone of regional annihilation, the impact effects spread across the entire planet through multiple physical mechanisms operating on different timescales. The first global effects manifested during the initial hour as seismic waves propagated through Earth's crust. Atmospheric shock waves circled the planet, and the highest velocity ejecta began falling on distant continents. Within hours, thermal radiation from returning ejecta would ignite wildfires on every continent. Within days to weeks, the atmospheric dust and sulfate aerosols would achieve global distribution, beginning the prolonged impact winter that would shut down photosynthesis worldwide. The extinction would not be limited to organisms near the impact site. It would propagate through every ecosystem, every food web, every biological community on Earth. The seismic waves traveled through Earth's crust at velocities of several kilometers per second, reaching North America within minutes and propagating to the most distant continents within the first hour. At the Tsunamis site in North Dakota, approximately 3,000 kilometers from the impact, seismic waves arrived within 13 to 30 minutes, generating powerful seesh activity in river systems that killed fish and buried them, along with falling impact spherules. Similar effects would have occurred in river systems and lakes across North America, as the seismic waves propagated outward from the Gulf of Mexico. In South America, the seismic waves arrived within 30 to 45 minutes, causing widespread ground shaking and triggering landslides in mountainous regions. Europe and Africa experienced the seismic disturbance within the first hour, while the most distant landmasses, Asia, Australia, and the far Pacific, felt the ground shake within 90 to 120 minutes as the waves completed their circuit through the crust. The atmospheric shockwave, a pressure disturbance, traveling through the air at supersonic velocities, circled the planet multiple times during the first several hours after impact. Unlike the blast wave that caused mechanical destruction near the impact site, the atmospheric shock at global distances was primarily an acoustic phenomenon, an immensely powerful sound wave inaudible to human ears due to its low frequency but capable of being felt as pressure changes by any organisms with atmospheric pressure sensitivity. The shockwave traveled at approximately 200 kilometers per hour through the stratosphere, completing its first circumnavigation of the planet in roughly 33 hours, then bouncing back and circling again in diminishing intensity. The passage of these pressure waves may have contributed to respiratory distress in large animals across global distances, though the effects were far less catastrophic than the regional blast wave near the impact site. The ejecta distribution pattern was determined by ballistic physics and stratospheric winds. Material ejected at the highest velocities, approaching or exceeding escape velocity, was lost to space or achieved suborbital trajectories that carried it halfway around the world before re-entry. This material began falling on continents thousands of kilometers from the impact within the first hour, creating meteor displays visible in daylight as fragments burned through the atmosphere. The impact spherules found at Tsunamis arrived within 13 minutes to 2 hours, providing a marker horizon that allowed scientists to reconstruct the timeline with unprecedented precision. Similar horizons have been identified worldwide, with spherule sizes decreasing with distance from the impact. Larger beads near the impact site, finer material at global distances. The thermal radiation from returning ejecta proved to be one of the most devastating global effects. As millions of fragments simultaneously re-entered the atmosphere across wide geographic areas, the cumulative friction heating raised atmospheric temperatures substantially. Computer models indicate that this thermal pulse was sufficient to ignite vegetation on every continent, initiating the global wildfires that would burn an estimated 70% of Earth's forests. The fires began first on continents nearest to the impact, North and South America, within the first few hours, then spread to Africa, Europe, and Asia as ejecta continued falling through the first day. Even Antarctica and Australia, at maximum distances from the Yucatan impact site, experienced ejecta re-entry and likely suffered widespread fires in the forests that covered their warmer, late Cretaceous latitudes. The wildfires created their own global effects through massive soot production. Charcoal layers in KPG boundary sediments worldwide contain chemical signatures indicating combustion of terrestrial vegetation, woody tissues, leaves, and organic-rich soils. The smoke plumes rose into the stratosphere, where soot particles joined the silicate dust and sulfate aerosols in blocking sunlight. Research examining the optical properties of impact-generated aerosols has revealed that soot from wildfires contributed substantially to the reduction in solar transmission, potentially accounting for 20 to 30% of the total atmospheric loading. The combination of dust, sulfates, and soot would reduce sunlight reaching Earth's surface to only 10 to 20% of normal levels, with the blockage persisting for months to years. The oceanic effects extended globally through multiple mechanisms. The mega tsunami, generated by the impact, propagated across the Atlantic Ocean, reaching coastlines of Africa and Europe within 12 to 24 hours, while wave heights decreased with distance, from over 100 meters in the Gulf of Mexico to perhaps 10 to 30 meters on transatlantic coastlines. The waves remained capable of causing substantial coastal destruction and penetrating far inland in low-lying regions. The tsunami reached the Pacific Ocean through passages around South America and through the Proto-Caribbean Seaway, though wave heights were further attenuated by the longer travel distances. Every coastal ecosystem on the planet experienced some degree of tsunami disturbance, with severity depending on distance from the impact, local bathymetry, and coastal topography. The injection of enormous quantities of material into the oceans, impact ejecta, wildfire debris, sediments suspended by the tsunami, and acids formed from atmospheric sulfur dioxide, began altering ocean chemistry within hours to days. The most immediate effect was physical disruption. The tsunami stirred coastal waters to unprecedented depths, suspending sediments and reducing light penetration for photosynthetic organisms. The thermal pulse from re-entering ejecta heated surface waters substantially in some regions, potentially causing thermal stress for marine organisms adapted to stable temperature regimes. The longer-term chemical effects would prove even more devastating as acid rain began falling globally, lowering ocean pH and creating conditions that would persist for decades. The atmospheric dust and aerosol loading achieved global distribution through stratospheric circulation patterns. The impact injected approximately 25 trillion metric tons of material into the stratosphere and beyond, creating the largest atmospheric perturbation in millions of years. The stratospheric winds, traveling at hundreds of kilometers per hour at altitudes above 20 kilometers, distributed this material globally within days to weeks. The dust remained suspended because the particle sizes were sufficiently small that gravitational settling was slower than vertical mixing by atmospheric turbulence. The sulfate aerosols formed continuously as the 325 gigatons of sulfur dioxide gradually combined with water vapor, creating new aerosol particles even as older ones were removed by precipitation. The impact of winter began within weeks as the accumulated atmospheric loading reached levels sufficient to block the majority of incoming sunlight. Temperatures dropped rapidly, with modeling suggesting decreases of 5 to 31 degrees Celsius, depending on latitude and local conditions. The polar regions cooled less dramatically because they already received less solar radiation, while tropical regions experienced temperature drops that brought them into ranges comparable to modern temperate zones. More critically, the reduction in light intensity shut down photosynthesis across vast areas. On land, plants could not generate sufficient energy to maintain growth or reproduction. In oceans, phytoplankton populations crashed as light levels fell below the compensation point where photosynthetic energy gain equals respiratory energy loss. Collapse of primary productivity triggered cascading extinctions through food webs worldwide. Herbivorous dinosaurs, hadrosaurs, ceratopsians, sauropods, and smaller ornithischians faced immediate starvation as vegetation ceased growing and existing plants were consumed or killed by freezing temperatures. These herbivores had enormous caloric requirements due to their large body sizes, requiring constant food intake to maintain metabolic function. As herbivores weakened and died, carnivorous dinosaurs, tyrannosaurs, dromaeosaurs, and other theropods lost their prey base. While carnivores initially benefited from abundant carcasses of herbivores killed by starvation, this resource was finite and non-renewable. Within months, the carnivores faced their own starvation crisis as the carcasses were consumed and no new prey animals were being born or reaching maturity. Marine ecosystems suffered parallel collapse. The extinction of photosynthetic phytoplankton removed the base of marine food webs. Zooplankton that fed on phytoplankton starved, followed by the small fish and invertebrates that fed on zooplankton. The cascade moved up through the trophic levels. Medium-sized fish, large predatory fish, and finally the marine reptiles at the apex. Mosasaurs, plesiosaurs, and other marine reptiles had survived multiple environmental perturbations during the Mesozoic, but the complete shutdown of marine primary productivity created conditions they could not overcome. The ammonites, marine mollusks that had flourished for over 300 million years, were driven to complete extinction, every species vanishing from the fossil record at the KPG boundary. The global extinction pattern shows remarkable consistency across ecosystems and geographic regions, indicating that the killing mechanisms operated uniformly worldwide. Approximately 75% of all species went extinct, including all non-avian dinosaurs, all pterosaurs, all mosasaurs, all plesiosaurs, and all ammonites. The extinction was size selective. Organisms larger than approximately 25 kilograms had very low survival rates, while smaller organisms fared substantially better. This size selectivity reflects the challenges of survival during prolonged resource scarcity. Large animals require more food, cannot enter small shelters, and have longer generation times that reduce adaptive potential. The survival patterns reveal which ecological strategies proved successful during the catastrophe. Scavengers and detritivores, organisms whose food chains were based on dead organic matter rather than living primary productivity, had significantly higher survival rates. Fungi thrived in the immediate aftermath as dead vegetation and animal carcasses provided abundant food sources. Insect populations probably crashed initially, but recovered more rapidly than vertebrates due to shorter generation times and broader dietary flexibility. Freshwater ecosystems showed higher survival rates than either marine or terrestrial ecosystems, possibly because detritus-based food webs in rivers and lakes could persist longer than photosynthesis-dependent webs. Mammals survived the extinction in substantial numbers. Despite being relatively rare and small-bodied during the Cretaceous, their survival likely resulted from multiple factors. Small body size reduced caloric requirements. Nocturnal habits and fur insulation provided advantages during the impact winter cold. Omnivorous or insectivorous diets offered more flexibility than strict herbivory or carnivory, and burrowing behavior provided shelter from thermal radiation and temperature extremes. The fossil record shows that while some mammal species went extinct, enough survived to provide the stock from which the great mammalian radiations of the Paleogene would emerge. Within 10 million years, mammals would diversify to fill the ecological niches left empty by dinosaurs, eventually producing lineages ranging from whales and bats to elephants and primates. Birds survived the extinction, though not all lineages made it through. Modern birds descended from a subset of theropod dinosaurs that possessed adaptations apparently advantageous during the catastrophe. Small body size, flight capability allowing access to diverse food sources, and possibly behavioral flexibility that permitted dietary and habitat shifts as conditions changed. The exact survival mechanisms remain debated, but the fact that birds made it through while their close relatives, other theropods including tyrannosaurs, did not suggest that the specific adaptations possessed by bird ancestors provided critical advantages. Crocodilians and champsosaurs, semi-aquatic reptiles, survived the extinction despite being relatively large-bodied. Their survival may reflect their detritivore-based diets, ability to fast for extended periods, aquatic habits that buffered temperature extremes, and possession of ectothermic metabolisms that required far less energy than the endothermic dinosaurs and mammals. Turtles showed similarly high survival rates, likely for comparable reasons. Lizards and snakes survived reasonably well, their small size and dietary flexibility providing advantages. Amphibians showed mixed results, with some lineages going extinct while others persisted. The marine realm showed stark contrasts between survivors and victims. Almost all large marine vertebrates went extinct. Mosasaurs, plesiosaurs, and various large fish lineages vanished entirely. Sharks and rays showed substantial extinction, but enough species survived to repopulate marine ecosystems. Bony fish experienced significant but not catastrophic extinction, with many modern fish orders tracing their origins to Cretaceous survivors. Marine invertebrates showed varied patterns. Ammonites completely extinct, belemnites extinct, but nautiloids survived, persisting to the present as living fossils. Bivalves, gastropods, and other shelled invertebrates showed substantial extinction but sufficient survival to maintain ecological function. The global effects of the Chicxulub impact thus operated through multiple mechanisms: thermal radiation, atmospheric dust loading, acid rain, darkness, cold, and starvation, each contributing to the extinction event. The combination of rapid-acting and slow-acting mechanisms ensured that few ecological strategies could provide complete protection. Organisms that survived the initial hours faced the prolonged impact of winter. Organisms adapted to the darkness and cold eventually faced the greenhouse warming that followed as the dust settled, but carbon dioxide remained elevated. The extinction was not a single event, but a cascade of environmental perturbations spanning years to millennia, each one removing additional species until 75% were gone. The story of how scientists discovered the Chicxulub impact and connected it to the dinosaur extinction represents one of the great detective stories in the history of geology. For more than a century after the term dinosaur was coined in 1842, paleontologists puzzled over the disappearance of these dominant reptiles from the fossil record. The extinction appeared sudden in geological terms. Diverse dinosaur communities present in rocks from the late Cretaceous simply vanished in younger rocks from the Paleogene, with no clear transition or gradual decline visible in most formations. Numerous theories were proposed: climate change, disease epidemics, competition with mammals, changing vegetation, volcanic eruptions, racial senescence, but none provided a satisfying explanation for the abruptness of the extinction or its global synchronicity. Across marine and terrestrial ecosystems, the breakthrough came in 1980, when physicist Luis Alvarez and his son, geologist Walter Alvarez, published a revolutionary paper in the journal Science, proposing that an asteroid impact had caused the mass extinction. The discovery originated from a seemingly mundane observation. A thin clay layer at the boundary between Cretaceous and Paleogene rocks in Gubbio, Italy, contained unusually high concentrations of iridium, a rare element in Earth's crust but abundant in meteorites. Luis Alvarez, who had won the Nobel Prize in Physics for his work on particle physics, recognized that the iridium anomaly could indicate an extraterrestrial source. Chemical analysis revealed iridium concentrations approximately 30 times higher than background levels in crustal rocks, a spike that demanded explanation. The Alvarez team hypothesized that a large asteroid, approximately 10 kilometers in diameter, had struck Earth at the end of the Cretaceous, vaporizing upon impact and distributing its material globally as a fine dust that settled to form the iridium-rich boundary layer. They calculated that an object of this size would release energy equivalent to approximately 100 million megatons of TNT, sufficient to trigger global environmental catastrophe. The theory was elegant and quantitative, but it faced immediate skepticism from many paleontologists and geologists who favored gradualist explanations for extinction. The debate that ensued would occupy the scientific community for more than a decade. Supporting evidence accumulated rapidly during the 1980s. The iridium anomaly was found at KPG boundary sites worldwide in marine sediments, terrestrial deposits, and locations spanning every continent. The global distribution of the iridium spike provided strong evidence for a single catastrophic event rather than gradual environmental change. Additional evidence came from the discovery of shocked quartz crystals bearing microscopic planar deformation features that only form under pressures exceeding 100,000 atmospheres. Conditions achieved naturally only during meteorite impacts or nuclear explosions. Shocked quartz grains were found in KPG boundary layers across North America and beyond. Their distinctive features, unmistakable markers of hypervelocity impact. The smoking gun, the impact crater itself, proved more elusive. An impact large enough to cause global extinction should have created a crater at least 150 to 200 kilometers in diameter. Yet no obvious candidate existed in the geological record. The solution to this puzzle came from an unexpected source. Petroleum geologists working for the Mexican state oil company Pemex had discovered a massive circular structure buried beneath the Yucatan Peninsula in the 1970s, but its significance went unrecognized for years. Geophysical surveys conducted for oil exploration had revealed a semicircular pattern of gravitational and magnetic anomalies centered on the town of Chicxulub, Puerto, indicating a buried structure approximately 180 to 200 kilometers in diameter. In 1990, geologists Alan Hildebrand and William Boynton connected the dots, publishing evidence that the Chicxulub structure represented the long-sought impact crater. The structure possessed all the characteristics of a large impact crater: the correct size to match the hypothesized impactor, the appropriate age dating to 66 million years, gravitational and magnetic anomalies consistent with shocked and melted rock, and most tellingly, the presence of impact melt rock and shocked minerals in samples obtained from the subsurface. The discovery of the Chicxulub crater transformed the impact hypothesis from controversial theory to established fact, though refinements and debates over details continue to the present. The subsequent decades witnessed an explosion of research, refining understanding of the impact event and its consequences. Seismic surveys conducted across the Yucatan Peninsula revealed the complete structure of the buried crater, showing it to be a complex impact basin with a well-developed peak ring, a circular mountain range of shocked granite, approximately 80 kilometers in diameter, surrounding the crater center. The peak ring's existence confirmed that the impact had penetrated deep into the continental crust, reaching depths where granite normally resides far below the surface. Computer simulations of crater formation processes demonstrated that peak rings form only in the largest impacts, when the transient crater cavity becomes so deep that crustal rock rebounds from mantle depths and collapses outward in a circular pattern. The most significant advance in understanding the impact came from a scientific drilling project conducted in 2016, which extracted core samples from the peak ring itself. The International Ocean Discovery Program, an international continental scientific drilling program, collaborated to drill into the buried crater, obtaining cores that preserved a minute-by-minute record of events during the first day after impact. The drill penetrated more than 1,300 meters below the seafloor, recovering rocks that documented the entire sequence of crater formation and modification. The cores revealed shocked granite ejected from depths of 10 kilometers or more, impact melt rock deposited in the first minutes after collision, and surge deposits laid down by water rushing back into the crater during the first hours. Analysis of the drill cores provided unprecedented temporal resolution of the impact event. The lowermost section contained granite that had been buried deep within the continental crust, rock that hadn't seen daylight in billions of years, now shocked by immense pressures and partially melted in just minutes. Above this sat more than 130 meters of impact melt rock and suvite, a chaotic mixture of melted and shocked rock fragments, deposited during the first minutes to hours after impact. The presence of shocked zircon crystals provided precise age dating, confirming that the impact occurred 66,043 million years ago, plus or minus 11,000 years. This date matches precisely with the KPG boundary layer found worldwide, eliminating any doubt about the connection between the Chicxulub impact and the mass extinction. The mammals that survived the extinction were small, mostly nocturnal, and occupied marginal ecological niches during the Cretaceous. Most were no larger than rats or small cats, with generalized body plans and unspecialized diets. But in the vacant ecosystems of the early Paleogene, these survivors found unprecedented opportunities. Within 10 million years of the extinction, mammals had diversified into forms ranging from tiny shrews to animals the size of bears. Within 30 million years, mammals had produced whales adapted to fully aquatic life, bats capable of powered flight, and the first primates, tree-dwelling animals with grasping hands and forward-facing eyes. The diversification continued through the Cenozoic, eventually producing the enormous diversity of modern mammals, including elephants, whales, bats, rodents, carnivores, and primates. The birds that survived represented a subset of the dinosaurian lineage, small-bodied, flying theropods whose ancestors had evolved flight during the Jurassic period. The extinction eliminated many bird lineages, but enough survived to seed the great avian radiations of the Cenozoic. Modern bird diversity. More than 10,000 species occupying niches from penguins swimming in Antarctic seas to hummingbirds hovering at flowers, traces back to the survivors of that catastrophic day. Birds remain the only living dinosaurs, a direct connection to the Mesozoic world that was so abruptly terminated 66 million years ago. The extinction opened. Ecological niches that had been occupied by dinosaurs for more than 160 million years, creating opportunities for the surviving lineages to diversify and adapt to roles previously unavailable to them. Mammals evolved to fill nearly every terrestrial niche. Small insectivores, medium-sized herbivores, large herbivores, small carnivores, large carnivores, and countless specialized forms. The evolution proceeded rapidly in geological terms. Within 10 million years, substantial diversity had been achieved. Within 20 million years, modern mammalian orders were established. This rapid diversification suggests that dinosaurs had competitively excluded mammals from these niches during the Mesozoic, and only their removal allowed mammalian adaptive radiation to proceed. The rise of mammals had profound consequences for Earth's ecosystems and ultimately for the evolution of intelligence. Mammals possess characteristics that proved advantageous in post-impact environments. Endothermic metabolism, allowing activity across wide temperature ranges, fur insulation for temperature regulation, live birth and extended parental care enhancing offspring survival, and relatively large brains supporting behavioral flexibility. These traits, which had been maintained through 160 million years of living in the shadow of dinosaurs, became highly adaptive once the competitive pressure from large reptiles was removed. The primate lineage, the group that would eventually produce humans, emerged in the early Paleogene as small tree-dwelling animals exploiting resources in the recovering forests. Early primates possessed grasping hands adapted for arboreal life, forward-facing eyes providing stereoscopic vision for judging distances while leaping between branches, and relatively large brains supporting complex social behaviors. These characteristics, initially adaptations for life in trees, would later prove critical for the evolution of tool use, language, and abstract thought in the human lineage. Without the extinction of the non-avian dinosaurs, mammals might never have achieved the ecological dominance necessary for primate evolution to proceed, and humans might never have existed. The Chicxulub impact thus represents a pivotal moment in Earth's history, a discontinuity that reset evolutionary trajectories and created the conditions for fundamentally different life forms to dominate the planet. The event demonstrates the role of contingency in evolution. The course of life's history depends not just on gradual adaptation to local conditions, but also on unpredictable catastrophes that can instantly eliminate dominant lineages and create opportunities for previously marginal groups. Had the asteroid missed Earth or struck a few minutes earlier or later, hitting a different location with different geological characteristics, the outcome might have been substantially different. The dinosaurs might have survived, mammals might have remained small and nocturnal, and the evolutionary path leading to humans would never have been traveled. The legacy extends beyond biology to planetary science and humanity's understanding of cosmic hazards. The Chicxulub discovery demonstrated that Earth exists in a cosmic shooting gallery where impacts are not theoretical possibilities, but documented events that have occurred repeatedly throughout geological history. The recognition of this vulnerability has prompted systematic efforts to catalogue near-Earth asteroids and develop potential deflection strategies. Modern astronomical surveys have identified thousands of near-Earth objects, though the catalogue remains incomplete for smaller objects capable of causing regional devastation if they struck populated areas. The Chicxulub impact serves as both a scientific case study and a cautionary tale, evidence that planetary catastrophes are possible and that humanity possesses both the knowledge to recognize the threat and, potentially, the technology to prevent future impacts. The scientific investigation of the Chicxulub impact has revolutionized understanding of mass extinctions and their role in shaping the history of life. Prior to the discovery of the impact, extinctions were generally viewed as gradual processes driven by slow environmental changes, competition between species, or evolutionary exhaustion. The Chicxulub discovery demonstrated that catastrophic events operating on timescales of hours to years could cause extinctions that appeared instantaneous in the geological record. This recognition has prompted re-evaluation of other mass extinctions in Earth's history, with researchers investigating whether impacts or other catastrophic events contributed to earlier extinction episodes. The methods developed to study Chicxulub iridium anomaly detection, shocked mineral identification, crater recognition through geophysical surveys, and high-resolution geochronology have been applied to investigate other potential impact events. Several impact structures have been identified and dated to times near other mass extinctions, though none show the clear correlation between impact and extinction that characterizes Chicxulub. The unique severity of the K-Page extinction likely resulted from the unfortunate combination of factors: a very large impactor, impact in sulfur-rich target rocks, impact in shallow water maximizing atmospheric injection of vaporized material, and potentially the stress already imposed on ecosystems by volcanic activity in the Deccan Traps of India. The recognition that mass extinctions can result from multiple interacting causes, impacts. Volcanism, climate change, sea level fluctuations has led to more sophisticated models of extinction processes. The hour before impact represents the last moment of the Mesozoic world, a world that had existed in recognizable form for more than 100 million years, where dinosaurs dominated terrestrial ecosystems, pterosaurs ruled the skies, and marine reptiles patrolled the oceans. The ecosystems of that world operated according to rules established through millions of years of evolution, with intricate food webs, complex ecological relationships, and species adapted to specific environmental niches. In 1 hour, all of that complexity was shattered. The accumulated adaptations of millions of years rendered irrelevant by environmental changes so rapid that evolution couldn't respond. The hour following impact witnessed the beginning of a cascade that would propagate through every ecosystem on the planet. The blast wave, thermal pulse, seismic shaking, and tsunami killed organisms across vast distances through direct mechanical effects. The wildfires ignited by returning ejecta consumed forests on every continent. The atmospheric dust and sulfate aerosols blocked sunlight for years, shutting down photosynthesis and collapsing food webs worldwide. The extinction proceeded in waves: immediate mortality from impact effects, starvation as food chains collapsed, cold stress during the impact winter, thermal stress during the subsequent greenhouse warming, and finally, the long-term ecological reorganization as survivor species radiated into vacant niches. The legacy of that hour extends to the present day. Every mammal alive today, from mice to elephants, from whales to bats, from dogs to humans, descends from the small, unspecialized survivors that endured the catastrophe. Every bird, from penguins to eagles, from hummingbirds to ostriches, traces its ancestry to the subset of theropod dinosaurs that survived. The modern biosphere owes its character to the removal of the dominant Mesozoic life forms and the subsequent adaptive radiation of the survivors. The Cenozoic era, the age of mammals, emerged directly from the ashes of the Cretaceous world. For humanity specifically, the legacy is profound. The primate lineage that eventually produced Homo sapiens emerged in the early Paleogene forests, exploiting ecological opportunities created by the extinction. The evolution of larger brains in primates, driven by the complex social and environmental challenges of arboreal life, set the stage for the eventual evolution of human intelligence. The development of tool use, language, art, science, and civilization, all the characteristics that define humanity, trace back through an evolutionary chain that would not exist without the extinction of the dinosaurs. In a very real sense, the Chicxulub impact created the conditions necessary for human existence. The hour before dinosaurs went extinct was, paradoxically, the beginning of the age of mammals and the ultimate precondition for human evolution. An asteroid 6 miles wide, traveling 45,000 miles per hour, struck Earth at precisely the location and angle to cause maximum catastrophe. In the hours that followed, 165 million years of dinosaur dominance ended, and a new evolutionary trajectory began. One that would eventually lead to a species capable of understanding what happened on that distant day, reconstructing the events in remarkable detail, and contemplating both the contingency of our own existence and our responsibility to prevent future catastrophes. The legacy of that hour will persist as long as mammals and birds inhabit Earth, a permanent testament to the power of catastrophic change to reshape the trajectory of life itself.